Day 4. Day 4 of our short course, and we are at lecture number 10. So today I would like to talk about interfacial thermal transport in lithium ion cells. In yesterday's lecture, one of yesterday's lectures, we learned that if I look at the various components of a cell, the anode, the cathode, the separator, the current collector, etc., each of them, we had said, has reasonably good thermal conductivity. The worst case thermal conductivity was that of the separator, and even that was about 0.5 watt per meter Kelvin. Whereas when we measure the overall thermal conductivity of the cell, it turned out to be 0.2 watt per meter Kelvin. And on the basis of that, we hypothesized that contact resistance between these materials may be playing an important role. Because if I just combine the thermal conductivities of these materials alone, it will not give me a value as low as 0.2. The reason why all 5 of these, when put together, perform even worse than the worst one is that they are not talking to each other. Is that the heat has a very difficult time jumping from one material to the other. And in fact, towards the end of the lecture yesterday, we said that there are a total of 4 contact resistances here. Current collector to anode, anode to separator, separator to cathode, cathode to current collector. And the question is, which of these resistances is the dominant resistance in this problem? Okay, so that is going to be the topic of our first lecture today. We will talk about thermal transport at the interfaces between materials inside lithium ion cells. Okay, so before I do that, I think there was somebody had asked this question about how do we measure the thermal conductivity of these materials. In the lecture yesterday, I had presented a technique for measuring the thermal conductivity of the overall cell, right? I want to briefly talk about thermal conductivity measurement at the scale of materials, and for that I will actually bring up a paper by Vivek Vishwakarma in 2014. He at that time was a PhD student in my lab, and he came to UT Arlington from IIT Ropar. He was a BTech student of Dr. Tyagi. And the point here is that the separator is a very thin material, sort of like this. What I've shown here is those paper rolls comprising the anode, cathode, separator, etc. So this is the positive, sorry, this is the negative electrode, the other one is the positive electrode, and in between is the thin separator. It sort of looks like a paper, or it looks like a thick polythene bag, sort of like that, right? And the question is, how do we measure the thermal conductivity of this body? Okay, there are several challenges in doing that. Mainly, when we were talking about the cell, when we were talking about the cell, we said that we'll put a thermocouple on this side, put another thermocouple on the other side, and measure the heat flux, right? Now, the smallest thermocouple that you can probably buy has a bead size of 200 microns, whereas my body itself is only 50 microns thick, right? So in other words, we are here entering the realm of microscale dimensions, where large sized bodies like a thermocouple will simply not work. So we had to come up with our own measurement technique to measure the thermal conductivity of the separator. And the way we did that was the following. I'll talk about the experiment first. So this is a good picture. The blue is the separator for which I want to measure thermal properties. Okay. In order to measure the thermal properties of the blue separator, think of a piece of paper. I want to measure the thermal conductivity of that piece of paper. What I did was, or rather Vivek, what Vivek did was that he printed a metal line, two metal lines on that paper. Okay, and printing of these metal lines is not that difficult, honestly. What is typically done is that you take the substrate, you put a mask on top of the substrate. So imagine if I take a aluminum sheet and make a hole in that sheet that corresponds to the shape that I want to print, right? And I place this mask on top of the substrate, okay, and put this in a metal deposition machine. Those are called, what are they called? E-beam evaporator. Titanium is deposited using E-beam evaporator. So basically there is a source of the metal, and you take an E-beam gun and you shoot on the source, which ejects the metal atoms, and they go all over, and obviously most of them will be intercepted by the mask, but some of them will pass through the hole in the mask, and the shape that you obtain on your substrate corresponds to the hole in the mask. Right? This is a common technique. This is easily done in any lab. You just need a couple of key pieces of equipment, but other than that, this is easily doable. Okay. So we deposited two metal lines. These metal lines are very thin. The thickness of these metal lines is, I think, 50 microns or so, and they're about 100 microns away from each other, and they're very long. Okay, so that if I draw a cross section, the cross section looks like this. I have two heater lines going into the plane of the paper. And then he said, okay, let me make electrical connections and let me pass a small amount of heating current of the order of microamps or milliamps. Okay, so imagine what will happen, and this entire experiment is being done in vacuum. Let me see if there is a picture of the experiment. Yeah, there is. So he does all of this on a glass slide. He suspends the separator material over two islands on the glass slide, and then he carries out his microfabrication so that in the end it looks like this. And you can see these are wires coming out to be able to pass current. Okay. He does not have a picture of the experimental setup, so let us skip that. But I want to go back to the schematic, and I want to think about what will happen as you pass heat through one of these heating lines. Clearly, the line through which you pass current will start heating up, right? So the temperature of this line will rise as a function of time. As this heat flows through the separator material, it's like a wave. After a little bit of time, that wave will reach the other line as well, correct? And the other line will also begin to heat up. If I sit there and measure the temperatures of these two lines as functions of time, then we developed a theoretical model for this problem, which basically said that T heater as a function of time should be given by this expression. And if I take the log of this This tells me that a semi-log plot of T heater as a function of time should become a straight line, and the slope of that straight line has information about the thermal properties of the body. This is sort of like the same thing that we did with the cell, right? With the cell also we predicted that the temperature should become a straight line, and the slope and the intercept of the straight line should give us information about its thermal properties. Similarly, we are predicting here that the heater temperature, when plotted on a log scale, will become a straight line, and the slope of that straight line gives us information about the thermal properties of the body. Moreover, what the theory was predicting, this is a good plot to look at. So what I'm plotting here is blue is the heater line temperature, red is the sensor line temperature, and black is the difference between the two. So you can see that both of them are rising, but after some time the temperature difference between the two becomes constant. And that constant value at large times gives us information about the thermal conductivity of the body. And also if I plot the heater temperature as a function of time, we also find that is also a straight line, and the slope of that straight line gives us information about the thermal properties of the body. Okay? This is a good example of designing your own experiment to measure thermal properties. Sometimes there are well-known techniques already available that you can mimic in the lab, like I had explained in the lecture yesterday. But if a technique is not available, if the material is too thin for me to use thermocouples and all that other stuff, then one has to design their own experimental measurement technique. Okay? Any questions on this? So I guess the long and short of it is that even the separator has a thermal conductivity of 0.5 watt per meter Kelvin. Using the paper that I had just presented, the measured value of the thermal conductivity of the separator turned out to be 0.5 watt per meter Kelvin, and it was a little surprising because the thermal conductivity of the cell itself was even lower than that of the separator. So from there we started asking ourselves, what do we need to do in order to measure the interfacial thermal resistance of this body. Okay, so let's take a simpler example. Suppose I have two bodies, A and B, that are nominally touching each other, in which case I have a resistance of the red, a resistance of the green, and in addition I also have a contact resistance. Okay, it's possible that the red is cathode, the green is the separator, and I want to find out the contact resistance between the cathode and the separator. And the question is, how do I do that? Okay, there are actually fairly sophisticated methods for taking such interfacial contact resistance measurements. For example, there is a method called time domain or frequency domain thermoreflectance. In short, called TDTR or FDTR, which people use quite commonly in order to take such measurements. This requires a fairly complicated optical infrastructure, which I'm not an expert at. So we thought of something simpler, something more engineering in nature. Okay, we said, okay, I have a problem with three resistances, correct? Our cathode, our separator, and our cathode separator at the interface. I am mainly interested in measuring or in determining this one. Yeah? Can I find out our cathode? How will I find out the thermal resistance offered by the cathode? Sorry? No, we are talking about thermal resistances here, keep in mind. Sorry, all of these resistances are thermal resistances. Okay? So in this course, unless I specify otherwise, resistance refers to thermal resistance. So remember that the thermal resistance of any body in one dimension is given by its thickness over its area and its thermal conductivity. This expression, by the way, is very similar to electrical. In the electrical world, what is the resistance given by in terms of resistivity? Rho L over A, right? Yes, rho L over A, which can also be written as L over A sigma. Rho is the resistivity, sigma is the conductivity. Folks, this expression and this expression, they are exactly the same. In the electrical world, we have electrical conductivity. In the thermal world, we have thermal conductivity. Okay, so to find out the thermal resistance of the cathode, I need to know its thickness, which I know. I need to know its area of cross section, which I know. I need to know its thermal conductivity, right? The thermal conductivity of just the material can be easily found out using the techniques, for example, that we had discussed in the last lecture. I can take my material, I can put a heat source on one side, I can have cooling water on the other side. Remember the whole experimental setup we discussed yesterday, and we can take temperature sensors. Chal raha hai na? I got a no internet message. So from here, I can use Fourier's law to measure the thermal conductivity of this material, right? So imagine I run an experiment in which I take only the cathode and measure its thermal conductivity and therefore find out our cathode. Then I run another measurement in which I take only the separator material, run this experiment only on the separator, so that I find out, so that I now know these two resistances. Okay? What should I do next? No, there is not a ready connection between thermal resistance and electrical resistance. Okay, remember that I have three thermal resistors in series. I have been able to find two of them by measuring the cathode and the separator alone. Now if I measure both of them together, that measurement will give me the total thermal resistance. Right? And if I know the total thermal resistance and two components of it, I can simply subtract them out to indirectly measure my contact resistance. In other words, If the total measurement turns out to be 100 and these two components are 10 and 40 respectively, then clearly the contact resistance must be 50, right? Just simple addition subtraction. So that is what we did. We said we'll measure the cathode first, we'll measure the separator next, and then we'll put them together and measure it then again and look at what happens to the total resistance when you put them together. That was the basic idea. Alright, let me switch to the paper in which I can discuss some more details of how this was done and some of the repercussions of the results that we obtained. So this was also Vivek's work, and as you can see, this was, I mean, this was Vivek and I, simple. The first paper that I showed, just him and I, right? The second paper is a bunch of co-authors. I was talking at that time with Ravi Prashar, who's a good friend of mine, a senior from my undergraduate years, and he helped us with some of the interfacial contact resistance modeling. There were some people involved from Oak Ridge National Lab and a collaborator, Pushong Liu, from the material science department, who helped us with the electrochemical measurements, and one of his students, Ziwei. I think none of them are where they were at that time except myself. So in this paper, we started by providing a justification for why these measurements are important, okay, and then we basically made the argument that I was making on my slides, that if I want to measure the resistance between the separator and the cathode, it is basically 3 resistances in series. If I measure 2 of them separately and I measure the total, then I can just subtract them out to find out the interfacial resistance. So to do that, we designed a very simple experimental setup in which we took 2 copper blocks. Why copper? Because copper has well-known thermal conductivity, and we drilled a number of holes in the copper blocks and inserted thermocouples on both of them, the hot side and the cold side. On one end of this, on the hot side, we inserted a metal, a thin heater. So through this heater, you can barely see, we can pass current in order to heat this up from one side. Okay, and on the other side, we drilled a big hole and connected it to a water supply, a cold water supply, and basically passed cold water. Okay, we were having a lot of difficulty seeing the cold water because water was transparent, right? And one day Vivek said, okay, and the water became red. No, just kidding. We took some other red dye and put a drop of the dye to be able to see the water. Okay, and then the most important thing is that in between the hot block and the cold block, we sandwiched the material of interest, whether it is the separator or it is the cathode or it is the sandwich of the two. Okay, so for now just imagine that this is only the cathode material, right? I have heat entering this copper block from the top and heat leaving from the bottom, picked up by the cold water and taken away, right? During this time, this heat has to pass through the cathode material to jump from the top block to the bottom block, right? This is a typical temperature versus time, temperature versus X plot based on the 15 or so thermocouples that we had. The red ones are in the top, the blue ones are in the bottom. By the way, folks, it's extremely important when we are trying to communicate technical information to others for it to look nice, clean and organized. See, I made several deliberate choices here. I chose to use red color for all the hot thermocouples. I chose to use blue color for the cold thermocouples. And my schematic is in the same color scheme as my plots are, right? My font sizes are big and easy to see and so on and so forth. And even this picture is pretty good if you print it on paper. Of course, if I zoom in, it will look grainy. But if you print it on paper, look at it at reasonable resolution, it looks pretty good. It is extremely important for all of us to not only do good work, but also communicate it well. In fact, in our lecture after lunch today, I will talk about technical communication in terms of writing and in terms of presenting. So I will share some of my experiences and a list of do's and don'ts that I have developed over the years about how to be an effective communicator in terms of writing papers, technical reports, etc., and in terms of presenting to your advisor, to your committee, to conferences and so on and so forth. Those are extremely important skills. Do good work is half the job done, present it well is the other half. So in the afternoon today, I'll share some of the things that I have myself learned over the years. Okay? Alright, so what does this give us? This tells us a few things. Firstly, the temperature distribution in each of these blocks by themselves, either the red or the blue, is very linear. Right? I'm able to fit it very nicely with straight lines in both of them. However, interestingly, there is a large temperature jump. There is a large temperature jump at the interface. What that tells me is that the thermal resistance at the interface is much larger than the thermal resistance of the blocks themselves. Which is not surprising, the blocks are made up of copper. Copper has high thermal conductivity, right? So copper is expected to offer very low thermal resistance, which is why the slopes of these curves are so low, right? But on the other hand, there is a significant temperature drop across this interface, which is essentially the thermal resistance offered by this material. Okay, let me go to my sheet for a second. The thermal resistance by definition is delta T over Q double prime. So if I would like to measure the thermal resistance offered by that sheet which I placed between the two blocks, let me go back here. If I want to measure the thermal resistance offered by this purple sheet, then I want to find out the temperature difference across that purple sheet and the heat that flows across that purple sheet. How will I find out the temperature difference across that purple sheet? It is this number, this delta T between the two curves. You see, if that sheet was offering zero resistance, then these two curves would have been a straight continuous curve. But the fact that there is a temperature drop here means that there is some resistance being offered by the sheet that I inserted between the two copper blocks. Right? So I can find out delta T from my measurement. What about Q double prime? How do I know how much heat is passing through the sheet? Sure. There are a few ways of doing that. If I measure how much current is passing through my heater, and if I have reasonably insulated around it, then the amount of heat passing downwards is equal to the heat that is being generated in the heater device, right? That is not always true. because some of that heat may very well leak here and there, right? Similarly, the amount of heat passing through the sheet can also be said to be equal to the amount of heat being removed by the by the water, right? But then again, it is also possible that some heat is coming into the system from here and there, and the two may not be equal to each other. The best way of finding out how much heat passes through this is by using the copper blocks as a reference. How much heat is passing through the copper blocks? At the top, the amount of heat passing through the copper blocks is given by K copper multiplied by dt dx, the slope of this line, right? The heat passing through the bottom copper block is given by K copper multiplied by the derivative of temperature in the bottom block, right? Remember we said very early on, Q equals negative K dt dx. The good thing is the thermal conductivity of copper is well known, and therefore if I multiply K copper by the temperature gradient in both blocks, then that gives me the amount of heat passing through the top and the bottom blocks, and that both of them must be equal to the heat passing through the separator. That was the basic idea in the paper. So having done those calculations, we can find out the resistance offered by this sheet of whatever that sheet is made up of. And then of course, once all of this is ready, I can repeat this as I had said for the cathode alone, then the separator alone, and then the sandwich of both of them. So by 3 experiments, I will have found out our cathode, then our separator, and then our total. And from there it is straightforward for me to find out our cathode separator. Okay? Any questions? We can. So this experiment in which we are doing these measurements, if I take this separator and if I wet it in the electrolyte and put it there, then I can account for the effect of the electrolyte. We had a lot of difficulty doing that. Those were early times. We didn't know how to handle electrolyte and so on, and that electrolyte of course would evaporate and so on. So our measurements were done on a dry sample.
Then there will be the thermal resistance which we are calculating. Value must be.
Yes, it must have affected it in some way, but we made the argument that since the thermal conductivity of the electrolyte is so low, it probably does not offer a good heat transfer path for heat to pass through. Okay. Looking back at it, this was certainly a weakness of this paper in that we could not quite measure the thermal properties in the presence of the electrolyte. What would it have needed for us to do it? We would have probably needed to do this in a glove box with saturated electrolyte conditions, which would discourage the electrolyte to evaporate, right? You do it in a dry environment, all the electrolyte will easily evaporate. But if you already have some electrolyte, volatile electrolyte all around this experimental setup, then the electrolyte will not have a reason to evaporate, right? And then we may be able to run these measurements on wet samples. Exactly, by creating a high, I wouldn't call it humidity, but high concentration electrolyte vapor in the vicinity of the sample. Yeah, that's a fair point, and we did get some critique of this paper along the same lines, that you're not really measuring the thermal properties in the presence of the electrolyte. Any other questions or comments so far? So let's go look at the results now. So this is sort of schematic of the experiment. Separator alone, and then the entire stack, and then only the cathode side. So 3 sets of experiments that allowed us to take these measurements. Here are the results. I want you to forget about the right side for now. Let's just focus on the left side. So what the left side does is that it talks about the various components of the total thermal resistance of the unit cell that I am considering. Remember, the unit cell comprises the 2 current collectors, the cathode, separator, and I am ignoring the anode side for certain reasons right now. I'm only focusing on the half cell, the cathode side half cell. And this table lists the measured values of the thermal resistances of each component. We did not bother to measure the thermal resistance of the current collector because they are made up of copper and aluminum. I have all the reason in the world to believe that their thermal resistances are extremely low. So that is why those thermal resistances are less than 1 watt microkelvin meter square per watt. Okay. The cathode offers a little bit of resistance. The separator offers a good deal of resistance, which is expected because the separator is made up of polypropylene, a polymer material, which typically has low thermal conductivity, right? But the majority of thermal resistance, about 88%, we found was coming from the separator cathode interface. So it turns out that the 2 resistances offered by the materials are sort of like this, and the resistance offered by the interface is sort of like this. This problem is dominated by interfacial resistance. Once the heat gets into the cathode or into the separator, it can get through it very quickly. But then there is a backup at the interface. There's construction going on there, which is why all the cars are lined up and there is a big traffic jam. And now, as a highway engineer, if I want to come in and try to improve the traffic, then where should I put my efforts? Should I put my efforts in the roads which are nice and smooth, or should I put my efforts in the road where there is a lot of potholes or there's construction going on? Clearly, where there is construction going on, right? That is where the heat is having a lot of difficult time in passing through, right? That gave us a hint that look, in order to improve the thermal performance of the cell, there is no point trying to improve either the separator or the cathode. Those roads are pretty nice and smooth already. There is a small patch of road where there's a lot of potholes. That is where I need to go and fill those potholes so that the overall journey for the heat can be as smooth as possible. So around that time, there were papers that were talking about adding carbon nanotubes to the separator in order to improve its thermal conductivity, or adding boron nitride, blah blah blah, to the cathode, etc. We said, folks, stop, there's no point of doing any of that. If in the best case you come up with some separator that has excellent thermal conductivity, you put nanotubes, graphene, whatever is the flavor of the day for carbon materials, you saturate the separator with it. In the best possible case, what will you do? In the best possible case, what will this 100 number become? Resistance 0, right? If you take a lot of effort, that resistance can be brought down all the way to 0. But even then, if this green thing becomes 0, the total thermal resistance still does not change much, right? You've got to put your efforts in the right place, right? You've got to put your efforts in the right place. And here, the thing that requires the most attention is the interface, not the material itself. And this is not uncommon. This is not the first time people saw interfacial dominance like this. In microsystems, when materials are very small, interfacial dominance is quite common, because imagine I have a material that is becoming smaller and smaller and smaller. Once it becomes small enough, then the heat can pass through it very quickly, but the interface continues to offer a problem. Here, the materials themselves are conducting enough, but the interfaces are very poor. And there are reasons behind that. Somebody asked me yesterday or the day before, how is the separator and the cathode put together? Is there some glue between them? Do we put some kind of epoxy between them? No, the answer is no. They are simply stuck together at high pressure. So those four or five sheets that make up the cell, we bring those sheets together. I think there was a picture in the other paper, right? We bring these sheets together and we basically clump them together with some pressure, and then we roll them into a cylindrical cell. We do not do anything to try and adhere them to each other. Why? Because any material that I place between them can hinder the flow of lithium ions. I want lithium ions to pass through in an uninhibited fashion, which discourages me from putting glue between the two, right? But the problem with that is that if you take two materials, no matter how hard you push them into each other, they may or may not adhere to each other in the true sense of the word. Right? If you have one material which is slightly positively charged, the other material which is slightly negatively charged, they will come together very nicely and they will adhere very well, and the heat will be able to transfer from one to the other very nicely. It all depends on the chemical composition of the interface, of the surface. If the two surfaces don't like each other, no matter how much you push them, they will never really intimately connect with each other. And we suspected that that is exactly what was going on here. So then, Ravi and Vivek and I, we asked ourselves, what could we possibly do to enhance this heat transfer problem? We had hypothesized that the poor contact resistance between the two is happening mainly because of poor adherence between the two surfaces. None of us were chemists, but we said, why don't we do something to improve the adherence between the two surfaces? About the same time, another student of mine was running experiments using DNA, and he was trying to take DNA and stick it to a glass slide in order to run some other experiments. And he had learned that in that world, they commonly use certain molecules called aminosilanes in order to stick the DNA to the glass. The idea being that aminosilane molecule has a slightly positive end and a slightly negative end, and therefore the DNA comes and sticks on one side, the glass slide sticks on the other side, and this molecule basically acts like a molecular bridge between the glass slide and the DNA, allowing the DNA to stick to the surface. So we said, okay, in the absence of any other expertise we have about chemistry and all that stuff, why don't we try that out? So we took our cathode, the blue thing, and we placed the aminosilane molecule on it. Okay, we were doing this completely blind. We took a molecule and a experimental recipe that was primarily developed in the world of biology, and we said, okay, let's try it on lithium ion cells. Okay. On the other side, we carried out a plasma treatment of the separator. So just stick it in a plasma, oxygen plasma for 5 minutes. That basically cleans up the surface and provides a slight positive or negative, I forget what, charge on that surface, right? And then we stick them together. So experiment A is the baseline. Experiment B is one in which we only do silane functionalization. C in which we only do separator plasma treatment, and D is in which we do both of them. Because our hypothesis was that when we do both of them, that is when we will get the best effect and we would have reduced the thermal contact resistance. Okay, so we do all of this, we go back to our experimental setup. Remember the one I showed about the 2 copper blocks? And we repeat this measurement. And by now this copper block is getting heavily used, right? We are running a bunch of measurements one after another on this copper block. Remember that every time we run this experiment, we have to flush the water lines, we have to allow this system to reach steady state, and only then take our measurements. So takes a little bit of patience to take these measurements, right? But having done all that, if we compare the results of the baseline experiment with the enhanced experiment, you can see here that the first 3 components of thermal resistance don't change, but the interfacial thermal resistance reduces quite dramatically. It reduces by about 4 times by introduction of that aminosilane molecule between the 2 surfaces. By doing so, I am able to reduce the contact resistance from 840 microkelvin meter square per watt to only 180 microkelvin meter square per watt, because of which the total resistance also comes down quite significantly, right? I'm able to get a significant reduction in the total thermal resistance primarily because I identified the rate limiting step and I focused my energy on reducing the rate limiting step. It is, if I go back to my slides, it is this biggest resistance that I must focus my energy on and not these itty bitty things, right? If I'm trying to save money and if I spend 10 rupees on chai every day and 200 rupees on cake every day, then I should be looking to reduce my cake consumption, not my chai consumption, right? That's what is happening here. Any questions?
How you can claim that this will not affect the performance?
That's a good question. Absolutely. So you see, one good quality of research is that you need to be able to preempt, you need to be able to guess what kinds of questions you will get. Okay, so any reasonably knowledgeable person, when looking at this, what kinds of questions he and she will ask, right? That way you can prepare yourself for those questions coming from your dissertation committee or from your job interview or whatever it is, right? And this is a perfectly reasonable question to ask. I have placed that aminosilane molecule between the separator and the cathode. What is the guarantee that the lithium ions will not be stopped by that aminosilane molecule? Well, we did not know enough chemistry to answer that question. So we said, let us build cells. One cell without the aminosilane molecule, another cell with the aminosilane molecule, and see if their performance is significantly different or not. Okay? And when we do that, the results are in the paper. This is a charge discharge curve and this is an EIS measurements. These are, I have not introduced these in a lot of detail, but these are basically characterization experiments to understand the nature of electrochemical transport in the cell. In other words, how good is this cell from an electrochemical point of view? Okay. I think Dr. Agrawal had referred to some of this in his presentations, right? A lot of the theoretical modeling that he had presented was focused on predicting the discharge curve. So here what we did was that we took these 2 cells that we had built, one with the aminosilane molecule, one without the aminosilane molecule, and then we charged and discharged those cells for a few cycles, for only about 10 cycles if I remember correctly. Okay, and we showed that the baseline experiment and the enhanced experiment had more or less, not identical but more or less the same discharge characteristics. The EIS curves were also not too different from each other. Okay, this does not prove by any means that the aminosilane molecule will absolutely not disrupt the lithium ion transport, especially over a large number of cycles. We do not know. I mean, these experiments were only done for about 10 cycles. In reality, a lithium ion cell is expected to charge and discharge thousands of times. We do not know if that aminosilane molecule will survive, stay there for that long, and therefore we do not know what the effect of the aminosilane molecule will be on the long term thermal and electrochemical performance of the cell. That experiment we did not do. In all honesty, that experiment remains to be done. We in our lab simply did not have the equipment to run cycling over thousands of cycles. That's a field of its own, and we simply were not equipped to do that. So for the purposes of this science-based investigation of a potential technique, we are not looking to solve the problems of the entire world. All we are doing here is to propose one possible technique for solving the heat transfer problem, right? We haven't even implemented it in real lithium ion cells, but there is some proof of concept that quite likely this is probably going to work. Yes.
How you created that? Did you compare with the commercial cell?
No, this was the baseline here is our own cells without the aminosilane molecule.
You have made it the flat C.
Yes, we made a split flat cell with an active area of the details are here. Using, yeah, so we used lithium anodes. We purchased lithium anodes because this was all being done on the cathode side. So the lithium anodes were the same. On the cathode side, we used a baseline cathode separator, and we used one including the aminosilane molecule.
That too without
No. This experiment was done with electrolyte. Of course, we need electrolyte in order to charge and discharge the cell. So this experiment was done in the electrolyte, and we found that the two were nearly the same.
all the fermentally sealing or
Everything was identical, and it was done using a standard process. So Fuxiang Liu, who's one of the authors, was the one who built the cells for us in his lab. He had that capability. So collaborations, folks, are important. For a fairly large project like this, there are multiple aspects of it. Heat transfer, of course, being the central one. But you need somebody with electrochemistry expertise. You need somebody with microscale heat transfer expertise. And we were fortunate to be able to pull a bunch of people together to be able to, write a decent paper. Okay. Of course, this does not solve all the problems of the world. Okay, there are several holes here. Why aminosilane? Why not any other molecule in the world? If you go and talk to chemists, then they will say, well, there are different candidates of bridging molecules that you can use to bridge these two materials, and the aminosilane molecule, which we basically pulled out of a hat simply because somebody else in our lab was running some other measurements using the same molecule. We perhaps got lucky because it gave us decent results, but who knows, there is some other molecule that could perform much better than our aminosilane molecule. So I'll address that question as well in another paper in a little bit, but are there any other questions?
there can be some effects at higher temperature on the
Sure, it is quite possible
can be composed.
that the bonding might deteriorate at higher temperatures. Yes. In some sense, this paper only opens the gate, right? I think a good paper, not saying this is one, but a good paper certainly leaves a lot of questions to answer. right? There is no paper in the world that will answer all the questions. But if there is one paper that says, oh, this is interesting, what about we do this or what about we do that? A good paper is one that opens up new lines of inquiry, right? Motivates you to investigate this direction and that direction. And certainly in our limited world, this paper in 2014 or 15 certainly played that role, that it allowed us to start asking all kinds of other questions related to heat transfer in the cell. Any other questions or comments here? Yes. Of? What is the thermal conductivity of aminosilane? Well, I don't know the bulk thermal conductivity of aminosilane, but keep in mind that here the aminosilane molecule is just a single molecular layer between the two surfaces. It's just one molecular thick layer between the two materials. It does not make sense to talk about the thermal conductivity of a single molecule, right? Thermal conductivity is a bulk property, right? But nevertheless, you have a good point in the sense that in order to understand the role of aminosilane in improving the thermal contact between the two materials, we have to look at what is happening at the scale of atoms and molecules. And that is what another student of mine did a few years later. I'll pull that paper and I'll show that as well. So in other words, we realized at this point that if I want to evaluate multiple candidate molecules in this job of bridging between the two surfaces, say I give you 10 potential molecules and I ask you which one of them will work the best. There are two ways of doing that. One is running all these experiments all over again for each of those molecules. And the other is to evaluate these molecules using simulations. We took the second approach in our work, mainly because by then Vivek had graduated and actually a lot of other co-authors on this paper had also sort of scattered away, and it was very difficult for us to rerun these measurements all over again. On the other hand, I myself did not have expertise in simulations, and here I am not talking about the simulations we've learned in our class. Those are continuum simulations. Those simulations apply to relatively large sized bodies, at least tens of microns thick or larger. Whereas what we are interested here is in a single molecular layer of aminosilane between two bodies, right? I need to look at how heat flows through atoms and molecules, not through materials. And the kinds of simulations you need at the scale of atoms and molecules is very different from simulations at the scale of materials, because at the scale of materials the governing equations are Fourier's law, q equals negative k dt dx, and so on and so forth, right? Those equations are actually continuum representations of heat transfer at the nanoscale. At the nanoscale, we need to look at what happens to an individual atom as you heat it up. As you heat up an atom, it begins to vibrate faster, because of which it pushes the next atom into vibrating faster, because of which that pushes the next atom into vibrating faster, and that is how heat flows. In order to look at this process at the scale of interest here, at the scale of an individual molecular layer, I need to do simulations that account for individual molecules. We didn't do that in our simulations yesterday, right? We didn't even worry about individual atoms and molecules. We just said, okay, this material has a thermal conductivity of whatever. That number that we assign sort of captures the behavior of atoms and molecules. Atoms and molecules that don't vibrate very fast and don't transfer the vibration very fast have low thermal conductivity. And atoms and molecules that do that transfer very effectively have high thermal conductivity. That is how we account for those atoms and molecules in our bulk simulations. But what we want to do here is to go down to the scale of individual atoms and molecules. Those simulations are called molecular dynamics simulations. MD simulations. Is there anybody here who does molecular dynamics simulations? No, not quite. That's different.
We tried some DFT.
DFT, exactly. Yes, yes.
Tried for some graphene oxide sheets for
Yeah.
absorption of toxicological assessments.
Mhm.
So we did it experimentally.
Mhm.
Then we have uploaded the X-ray diffraction data and the chemical kinetics data to examine how effectively the graphene sheet can act as a micro observable filters for pharmaceutical effects.
Sure, absolutely.
So we are trying to monitor.
Yes, and that happens at the scale of individual graphene molecules. You have
Single sheet of.
exactly single sheets, absolutely. So the idea behind molecular dynamics is very similar to billiards. Is that what it's called? Billiards, pool, snooker.
Yes.
Yeah. So atoms and molecules in some way behave similar to billiard balls on a billiards table. Okay. The temperature of any atom or molecule corresponds to its speed. The faster a molecule is traveling, the higher is its temperature. So imagine if I take that, what's it called? Stick. Sure. If I take a stick and if I hit this ball at a high speed, then this ball will travel and it will collide with this ball, which will cause the two balls to scatter. This process causes a transfer of momentum from this ball to the other ball. This other ball will also then travel and randomly hit another one and transfer its momentum to that, and so on. And pretty soon, a bunch of these balls which were initially stationary will now begin to move. Right? From a heat transfer point of view, this process is exactly what happens and is responsible for the flow of heat. When I take a stick and hit this ball with a stick, I am basically applying a high temperature on this side, right? And this is at a low temperature, but as time passes, the heat flows from the hot side to the cold side. And how is the motion of billiard balls governed? What is the fundamental law behind determining or predicting how these billiard balls are moving? Sorry? Momentum conservation, exactly. If I have two balls that are traveling, they come and hit each other and move their own ways. A1, B1, A2, B2. One refers to before, two refers to after. Then the total momentum must be conserved, right? So momentum of A coming in plus momentum of B coming in, and these are vectors, must be equal to the momentums of A and B added together, right? I can apply this very simple principle on billiard balls. I can also apply this very similar principle on individual atoms and molecules, and I can see how they will travel around and they will transfer heat from one side to the other. That, in my limited, crude knowledge of molecular dynamics, is all that there is to it. Molecular dynamics, however, is much deeper, okay, and I've only given you like I mean, I'm sure an expert can take a whole GIAN course on molecular dynamics simulations and more, right? Myself not being an expert, I sat on this problem for quite a while and actually talked to quite a few potential collaborators, and things quite did not work out. Okay?
Because every tool will be having a different significance.
Yes.
It cannot predict that, it cannot able to execute
Yes.
Anyways, ours is a different set of applications. We are not
Correct.
into batteries, but we are into different set of applications.
Right.
The degradation efficiency and the computation. So we tried more than 6 to 8 months for different tools.
Correct.
Gaussian we tried, Silicon we tried.
Yes.
And finally, we tried another version of Gaussian.
Yes.
And it requires a supercomputer.
Yes.
Not with the ordinary laptop.
Yep, absolutely. So there you go. There are challenges in doing this, and how we overcome these challenges is a funny story. So I was spending a summer at the Air Force Research Lab in the US, and I had enrolled my little kid. He was, I think, 2 or 3 years old at that time, at a daycare there. I was dropping off my kid at the daycare where I saw a familiar face, and I couldn't quite figure out who that guy was. But he was dropping his kid there every day. In a couple of days, we figured out who he was. He was 1 year junior to me at IIT Delhi. Do you remember uh, Vikas Varshni, Electrical Engineering Department, 1 year junior to us? 1 year junior to us. Biswadeep Bose, his group, his year, Biswadeep Bose's year. So I happened to run into him out of the blue in some unfamiliar place, and we were of course extremely happy to see each other, and we met, families met, etc. We are still very good friends and all that. And then we started talking about what we do, right? And it turns out that he is a good expert in molecular dynamics simulations. So I went to him and said, Vikas, we've got to work on this. We've got to figure out how to solve this problem. I really want to. And he said, yeah, of course, I'm happy to help, and so on. And one thing led to another. I'll show you that paper. This was in 2015. The paper with Vikas was much later. As I said, I sat on it for a long time, and then the work itself took a little bit of time to happen. What am I looking for? I'm looking for Dhakane. There. So that happened in 2020. Remember, the goal was for us to somehow get a confirmation of the experimental measurements. Experiment said that if you put an aminosilane molecule, the contact resistance will improve. So I wanted to confirm that through simulations, and as a bonus, I also wanted to be able to carry out a comparison between different materials, material A, material B, material C, which one of them offers the best contact resistance between the samples. Who are the students here? Abhijit Dhakane was at that time a master's student in my lab. He left after his master's and he joined Oak Ridge National Labs for his PhD, and he is now about to finish his PhD. And of course there's Vikas, and there's a couple of other people who Vikas introduced me to. So he said, you know what, we need another expert to work on this part of the problem. So he talked to his friends, and we all got together and did this work. And I'll show you, the idea is very simple, and it is very similar to the experiments that we had done. In all honesty, I don't know more than 10% of this paper myself, because it was all done by other experts. And Abhijit, the lead student, to give credit to him, he was able to learn a bunch of these things, a bunch of these simulation techniques, talking to Vikas, and he was able to lead this work. So in some sense, I was just the facilitator. I just got all the people together on the same table, and then they all got talking. I'll show you. Yep. So this is the molecular dynamics simulation that we had done. We placed individual molecules of lithium cobalt oxide on one side, which is the cathode, amorphous polyethylene on one side, which is the anode, sorry, the separator, right? And we placed a very thin layer of, actually there is no, this is without the bridging molecule. There is nothing in between. The two are touching each other directly. And I think if I go further down, I now have a thin layer of the aminosilane molecule between the two. Okay. I will perturb this system from the right. So from here, I will assign a high temperature I will basically take the stick, the billiards stick, and I will hit all these molecules and I will force them to start moving very fast. And they will transfer their energy to the next ones, and so on. And that heat will pass through the aminosilane molecule layer and go into the polyethylene. This is sort of like playing billiards with molecules, and this is very similar to the experiment that we had done. In principle, the experiment and the simulation, they both are doing the same thing. Yes?
Where you are, in the experiment also there you are using the lithium cobalt.
Correct. Yes. Yeah. Actually, I don't remember. I'll have to go and confirm. Maybe there was a slightly different chemistry there. And the reason why we chose lithium cobalt oxide here was that these simulations need the, I think they're called the force fields, the force potentials or something like that. And those we were able to only find for lithium cobalt oxide, not the other molecules.
The variables required should be different.
Yes, the variables required here are not thermal conductivity, heat capacity, density, etc. Those are bulk values. The properties needed here are the intermolecular potential force field, Lennard-Jones force field, something like that, of these molecules. You can see I'm not an expert here, but you know, if you don't know something, what do? You go and talk to people who know. And if one of them turns out to be your batchmate, that really helps. Yes? No, electron mobility is not considered here. There is no flow of electrons here. Hmm. Yes, in general, heat is transferred by both electrons and phonons, but here the contribution of electrons is zero because polyethylene and lithium cobalt oxide are both insulators. They don't, you can't pass current through polyethylene. Yes. हाँ 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 I should have said that. So the billiard ball example that I showed was not in the case of a gas, they are the atoms themselves. Gas के atoms तो travel करेंगे here and there. Solid के atoms don't travel here and there, and therefore the balls that I showed there are not the atoms themselves, but they are the vibrations of those atoms. In fact, those vibrations are called phonons. Lattice vibrations, exactly. वो जो lattice vibration होती है, that is the one that travels. कि आपने इसको vibrate किया, उससे कारण ये vibrate हुआ, उससे कारण तीसरा vibrate हुआ, तो आपकी जो vibration है वो travel कर रही है. And so you imagine as if those vibrations are represented by a particle, an imaginary particle. That imaginary particle is called a phonon. So when that vibration travels, we imagine as if there is a particle called a phonon which is actually traveling. Okay? Any other questions here? So once Abhijit was able to do the baseline simulation without anything in between, and then he was able to do the simulation with the molecular layer in between, then he said, okay, let me go on a hunt for different bridging molecules and see if I can implement each one of them in my simulations. These are fairly time consuming simulations as you had indicated, right? Our ANSYS simulations yesterday finished within a few minutes. This setting it up takes several days. I see you smiling, and the computational cost of this is not measured in terms of few minutes on a laptop, right? This is several hours on a supercomputer sort of a deal, because we are talking about individual atoms and molecules moving around and solving those complicated equations. Okay, this by itself, by the way, is a very rich field. I just don't have that expertise, but you know, there are people who have built careers out of molecular dynamics simulations for a wide variety of different applications, not just heat transfer. So I think these are the three molecules that he had he had considered, and you can see that a lot of these plots are very similar, and the whole flow is very similar to the experiments, right? We take two materials, stick them next to each other, heat up one side, cool down the other side, do this measurement of temperature versus X, and find out this delta T, right? The simulations and the measurements are walking along similar lines. And when he did that, let me get to the right plot here. I guess we can look at this. He shows that compared to baseline, if you have 10 layers, 20 layers or 30 layers of aptase molecule, which is that aminosilient that I keep talking about, the thermal conductance, sorry, we need to flip our thinking. He's plotting conductance, not resistance. So, do I want the conductance to go up or go down? I want it to go up, right? Sorry about this. We really should have. I think this community talks about conductance rather than resistance. So, the baseline conductance was about 100, and then when he started adding these aptase molecules, it jumps up to about 300 or even 400 megawatt per meter square per Kelvin. So, in principle, the improvement that our experiments showed are also seen in molecular dynamics simulations. Here, the best possible improvement was about 250% with the APTS molecule. He tried it with another molecule and he found that, yeah, there is some improvement, but it's not great. So he has effectively developed a tool which can evaluate and compare the performance of different molecules before you even take the effort of purchasing these molecules, setting up your experiment, running those measurements, taking the data, analyzing it, etc. Before you do any of that, you can run this simulation, and the simulation is able to help you say, you know what, don't even worry about that molecule. It's probably not going to work. But these two molecules which are showing good promise in my simulations are the ones that we should probably focus on. Right? None of these simulations capture all the real physics of the problem. The real problem is much more complicated. It has binders, the surfaces are rough, all kinds of real world considerations exist in the real thing, right? All of this, the experiment, the simulation as well, both of these are idealizations, approximations, but nevertheless, at the very least, these point us in the right direction. These tell us no point looking at this molecule. You've got to focus on the APTS molecule. And this one is actually very poor. In this one, the improvement is, there's hardly any improvement. In fact, it might even get worse. And so, from this we concluded that one specific molecule is the one that we should be focusing on. This paper I think has gotten quite a lot of traction. There are other papers that have built upon this work, molecular dynamics, to understand the molecular bridging between materials for lithium ion cells. I know there's at least one more paper in which they presented how hydrogen bonding between the two surfaces can help improve thermal transport between the two. And of course, going back to one question that you raised, this is a purely thermal simulation. This does not address how the transport of lithium ions will be affected by the presence of that molecular layer.
Even electromagnetic are also not
present here, yes. God knows this problem is already complicated with 3 molecules, adding another one and motion, right? And the transport of lithium ions, which is probably governed by a different set of equations, will probably make this simulation quite complicated. But I suspect that if a PhD student takes this up from start to finish, this would make for a very beautiful PhD dissertation, right? It's a difficult problem, but give enough hard work for a few years, I think it can be solved. Okay, all right. We are almost done with our time here. Is there anything else that I want to say here? No, I think I think I covered most of the stuff that I wanted to. So let's take a break, and after the break, Dr. Chandrasekhar Sharma will give a seminar on his perspective on thermal management of batteries and other devices. All right. So let's be back in an hour. This time is not right, yeah. Let's be back in an hour. No. Sorry, half an hour. Half an hour. Let's be back in half an hour, and after that will be the seminar by Dr. Sharma. Yeah. We'll start. Okay. So please settle down. Okay. Welcome to this lecture. So in this lecture, we will look at some applications of heat transfer related to microelectronics and battery thermal management. So I would like to start with what we all see in our daily lives. So we all deal with various kinds of computing systems, right? You have laptops, smartphones, right? And all these are powered by various configurations of microprocessors. So these are our daily use devices, but then there are also devices that we don't see. These are data centers. These are large computing systems, okay, and they are using a different class of processors, okay. So this is all in the current day and time, but how have we reached here? So we can trace back the development of these computing systems to as far back as mechanical computers in the 1600s and the 1800s, then leading to punch card based devices, okay, which became very popular, and IBM commercialized them in the 1950s and 60s. And then the next tranche of development we can relate to relay based computers, which were electromechanical based around the Second World War. And Second World War time also saw development of these large relay based systems, okay, where eventually relays were replaced with the vacuum tubes, okay. But then the major breakthrough comes in the form of invention of the point contact transistor in 1947, okay, and that leads eventually to the development of the integrated circuit. So transistors were initially connected with individual wires, but then it was realized that this is not feasible, and then somebody figured out that okay, we can integrate all the components of a microelectronic system on a single silicon wafer, okay. And from here the development of microelectronics starts. So initially the cost of all these devices was very high, but then the defense and aerospace programs of United States helped to scale up the production, leading up to the first microprocessors in 1971, Intel 4004. This is the first microprocessor, okay. Around the same time, Gordon Moore, you may have heard his name, Moore's law. So he made a prediction in a short article that as time progresses, we would be able to integrate more and more transistors and at lesser and lesser cost in a given chip. And this was his prediction. And what happened was that the microelectronics industry took it up as a challenge, and it became a self-fulfilling prophecy, okay. And here is what we have seen in the last
many decades. So here is your first commercial microprocessor, Intel 4004, with just 2300 transistors. And this data is not updated, this is up to 2018, but even in 2018 we have processors with a few billion transistors, okay. And this has all been made possible through miniaturization. So here what you see is a schematic of a transistor, okay, and this is the gate configuration. So here the gate is around 1 micron in 1974. By 2005 it reduced to 35 nanometers, and after 2020 we are seeing length scales of the order of 10 nanometers, okay. So but all this has to be powered up somehow. In the mobile computing devices it has to be powered up by batteries, and at the same time whatever heat is getting generated, that has to be also safely dissipated. So here we talk about the thermal design power of a device. So thermal design power means that it is the maximum sustained power that a microchip can dissipate without violating the limits of junction temperature. So junction temperature is the temperature of each individual transistor junction, right, and there is a upper limit of temperature beyond which these transistors will not be able to operate. They will not be able to switch between 1 and 0 state, right, and there will be some degradation of physical degradation of the material. In addition to that, we also worry about the non-uniformity of heat dissipation. So if this is a microprocessor, so this is an IR image of a real microprocessor, and you can see that some areas are blue, some are yellow, and there are also some red spots. So red means high temperature, okay, and this is a distribution of the temperature, and you can see that there are small hot spots in a processor, and the thermal management needs to take care of not only what is the total heat being dissipated, but what is the distribution of that heat dissipation, okay, because let's say if you have, let me go back, can I go back somehow? Okay, yeah. So if you, let's say if you design for average heat flux, then you may miss the temperature hotspot here, okay. Okay, so this is a typical cross section of a semiconductor device. At the bottom you have the transistor layer, and these are the interconnect layers, how these transistors are connected, right. So now why do we worry so much about thermal management? So in the semiconductor devices, as the temperature rises, like a typical chemical reaction, as you would have seen in thermal management lectures in the course for batteries, new chemical reactions and physical mechanisms will trigger, okay. So for example, if the temperature of the device is high, it can lead to electromigrations. So the interconnects between the microprocessors, so there electrons can migrate and they can physically start displacing the atoms, and that can eventually lead to a loss of contact in a interconnect, and the processor can stop working. Similarly, there can be thermomechanical stresses developed due to repeated cycling of high and low temperature, and that thermal stress can lead to delamination of different layers if the cycle amplitude is large, okay. Then there are also gradual wear outs of the gate material, like a prolonged exposure to high temperature, and there are a host of other mechanisms also, right. So electronic engineers always worry about this. So as thermal engineers, we have to take care that the temperature of the device is below the specified temperature limit during the lifetime of the microprocessor. Okay, now as I mentioned, all these computing devices have to be powered somehow. So data centers, they have the continuous supply, but mobile devices like the laptops and the smartphones that you are carrying, they are powered by the lithium-ion batteries, and you would have seen a lot of discussion in this course, and I don't think I need to spend time on this part, okay. So this working principle would also be very clear to you, and the adverse effects you would have already seen in Dr. Ankur's lectures. Okay, so I'll skip this part. So now I'll come to a few strategies of thermal management that are applicable to both the microelectronics as well as the batteries. Okay. So overall we can think of that in heat transfer what we are trying to do. We are going to use a fluid that carries away the heat to the ultimate heat sink while keeping the temperature of the device within a certain limit, and we can make an overall distinction. So one major distinction that we can make is single phase cooling and phase change cooling. So by single phase we mean that the coolant fluid is not undergoing any phase change, okay, and in phase change it is going to undergo some kind of phase change, right? Either it can be boiling or evaporation and so on. So let us look at first single phase cooling. So what are the coolants that we can very intuitively think of? Air and water, right? So this slide is somehow not coming up. So let me think of why one would prefer air and why one would prefer water as the coolant, right? So whenever we think about batteries and electronics, water is not compatible, right? But if we provide sufficient sealing for the flow of water, then water can also be used. But why would one prefer water over air in certain situations, right? So if you compare the density, the specific heat of air and water, so what you will find is that per unit volume, flow, heat capacity of air to that of water, that has a ratio of approximately 1 over 4000. So per unit volume of flow, per unit meter cube per second of flow, water can absorb 4000 times more heat, right, for the similar temperature rise, right. So why I am talking about per unit volume? So any coolant that has to be circulated to cool the batteries or the microelectronics, that has to be pumped in some way, right, and that pump is going to require its own power, right, and that is a drain on the overall system. And how do we calculate the pumping power? It's the pressure drop in the system multiplied by the flow rate, right. So as a thermal engineer, I also need to worry about how much pumping power I am ready to spend to circulate the coolant through my device, right. So I would like to keep the pumping power as low as possible for a given level of heat flux that I want to dissipate. And if a coolant fluid can carry away more heat per unit flow rate, that is better, okay. So cooling with water, it's not new. Proof of concept has been demonstrated more than 40 years back. So this is a very seminal paper on microchannel heat sinks cooled with the liquid water. So here you have small microchannels, okay, and water is flowing through it. There is heat flux coming from below, and that heat flux can be dissipated by the water flow, okay. Now one question that you can think of is why we need microchannels, okay. So as we are miniaturizing the devices, right, so as I mentioned, the electronic devices are getting miniaturized, right, at the same time your fluid systems are also getting miniaturized, to keep pace with the electronics, right. So the heat sink, as the microprocessor starts to become small in terms of the area that it occupies, I also want a small heat sink there to be accommodated over the processor, right. So now at those small length scales, as the fluid flow gets miniaturized, turbulence becomes unavailable to us, right. So we are stuck with laminar flow, okay. So now I can generate turbulence at small length scales also, but that would require immense pumping power, which is not feasible in terms of practical usage, okay. So how to increase or how to maximize the heat flux while staying in laminar flow? So you would know that for laminar flow in a closed duct, the Nusselt number is a constant. That is, it is not a function of the Reynolds number. So whatever flow rate is there, as long as you are in the laminar flow, the Nusselt number will stay constant, okay. So now Nusselt number is H d by k is a constant, right. So here H is your heat transfer coefficient, d is your hydraulic diameter, and k is the thermal conductivity of the fluid, right. So this means that my heat transfer coefficient is inversely proportional to the hydraulic diameter. So if I reduce the hydraulic diameter, I can increase the heat transfer coefficient, right. This we know from undergraduate heat transfer, right. So that's why I would want my coolant to flow through small microchannels which have small hydraulic diameter, so as to lift up the heat transfer coefficient that is available for heat transfer, okay. And if the heat transfer coefficient is high, then the same heat flux can be dissipated while keeping the temperature of the device low, okay. So that is why you have the you see the use of microchannel heat sinks, okay. So when we talk about microchannel heat sinks, so overall what will be the architecture? You will have a duct that is bringing in the coolant is distributed through the microchannels, and then the hot fluid goes out, right. But here it brings up another technical challenge, that how the flow is getting distributed in different microchannels. You would want the flow to be equally distributed, but because of the nature of flow, the flow distribution is non-uniform. So here this curve indicates uniform distribution of flow. So here the normalized flow rate is plotted with the microchannel number. So instead of a uniform distribution, you have non-uniform flow distribution with less flow near the center of the channel, near the center of the microchannel array, and more flow towards the boundaries, okay. So this is not ideal, right. So here then what is done is that you change the configuration of the inlet and outlet ducts. You make the inlet ducts converging, the outlet ducts diverging, and then the flow distribution starts to come close to the uniform distribution, okay. And this methodology is now applied over in many thermal applications, okay. Now if I am forcing a viscous fluid like water to flow through microchannels, there is going to be large pressure drop, right. So how can I minimize that pressure drop, okay. So as I mentioned, flow of water through microchannels has been demonstrated 40 years back, right, but the pressure drop is large in such a architecture. So what can I do there? So here another innovation comes in, that is that in the traditional microchannel, the fluid enters, traverses the entire length of the microchannel, then flows out. But what we can do is that we let the fluid come in, but then we divide the fluid into multiple streams, and each stream traverses only a small distance of the channel and then it comes out. So the flow length in the microchannel gets limited and this significantly reduces the pressure drop. Okay, so this is a schematic of how it can be done, but in reality this is the architecture. So here you see two layers of channels. One is this, so here the heat flux is coming like this. So this is the first layer of micro channels and this is a layer of mini channels. So these are not micro channels, these are ducts of millimetric dimension. Here the micro channels will be of the dimension of, let's say, 100, 200 micrometers, but these will be of the order of, let's say, a millimeter or so. So what these ducts are doing is that these ducts are distributing the liquid in the microchannels. So if you see here, the liquid is coming in and then it is distributing in on towards both sides, dividing into two streams. It is flowing a small distance and then coming out. So you have alternative inlet and outlet ducts here. This becomes more clear here. You have the inlet duct, this you have the outlet duct. The fluid comes in, flows into the microchannel, traverses this small distance and comes out. Okay, so this configuration is called as manifold microchannel heat sink. So this is the manifold and these are the microchannels, and this configuration achieves high heat transfer efficiency and low pressure drop. So you get the best of both the worlds. Okay, and another thing that helps in improving the heat transfer efficiency is that if you look here, the liquid is coming down and impinging into the channel. So this forms a configuration of a impinging jet. So you get the benefit of impinging jet heat transfer, you get the benefit of flow through the microchannel, and because the flow length is minimized, it reduces the pressure drop, overall pressure drop. So the pressure drop is lowered, heat transfer is improved, and that is what any thermal engineer would be looking for. Okay. Okay. So this is just a electron micrograph of a realistic configuration. So here what you see is this is the manifold layer and this is the microchannel layer. Okay, and this is a cut cross section of this device. So what has been done here is the microchannel layer has been formed in silicon and the manifold layer is also formed in silicon, and these are bonded together, and so you have a continuous liquid path. So here I hope you understand that here we are looking at the side wall of the microchannel. So the flow comes like this, it traverses like this and goes up. Clear? Okay. Okay. Now, as I mentioned earlier, that at the small length scale we are stuck with laminar flow. Okay. So one option to increasing the heat transfer efficiency in case of laminar flow is to reduce the hydraulic diameter. Another thing that we can do is introduce some instability in the flow. Okay. So for that we utilize the principles of flow instability in case of flow over bluff bodies. So here you see flow over a cylinder at different Reynolds numbers. So here the Reynolds number is less than 4, you increase the Reynolds number slightly. So at small Reynolds number the streamlines are nicely following the profile of the cylinder. At slightly higher Reynolds numbers you start getting some flow separation, right, and you have this vortex formation. But when the Reynolds number goes above 40, these vortices start to shed and then you have a vortex shedding which is periodic in nature. Now this vortex shedding can be utilized to increase heat transfer, and how we can do that? Okay, this is a schematic showing the vortex shedding from a cylinder. Okay, so here is a description of a heat sink where there are no microchannels, but there is a forest of these small micro pin fins. The flow is entering from one side, exiting from the other side, so it is flowing, let's say, into the plane of the board through these for micro pin fin arrays. These are called as micro pin fins. Okay, and you can have different arrangement of these pin fins, realizing different levels of efficiency. So here you see a plot of pressure drop versus Reynolds number. So up to a certain Reynolds number, the plot has a linear profile, which is expected for any laminar flow. But after a certain Reynolds number, the profile changes. Why is that happening? So beyond this Reynolds number, vortex shedding is starting, and that is causing the flow to become unstable. Okay. So if we look forward, so here are the streamlines of flow when the Reynolds number is small, and you can see here in between these micro pin fins, the flow behaves as if it is flowing through a micro channel, and in these between these pairs of micro pin fins you have these recirculation zones. Okay, but as you increase the flow, these recirculation zones become unstable and they start to get oscillated like this, and they start to disturb this flow also, and that leads to a continuous vortex shedding, and that improves the heat transfer. So here this is a temporal map of the velocity profile along these three lines. So like here if you see these three curves, the velocity profiles are changing as we are proceeding in time, and they keep on switching between each other. Okay, so the flow essentially, the flow looks like this. It starts to carry away some of these recirculation zones, and let's see if this video plays. Maybe I can come out of the. Okay, let me see. Okay, unfortunately the video is not playing. Yeah. Anyway, so what you would see here is a flow that is oscillating laterally. Okay, so in single phase flow you can do lot of things to improve the heat transfer, okay, by introducing certain instabilities or reducing the overall length scale of the flow. How I am doing in terms of time? Okay, we have time. Okay, so any questions so far? Yes. Yes, in that case the vortex shedding will be more, but the pressure drop will also be high. So then you have to take a call in terms of the trade-off. That are you, for the increased pressure drop penalty, are you getting a higher increase in the heat transfer?
Just a little bit.
Yeah, there are many different configurations that have been tried of even the staggered pin fins also. Even the profiles of these pin fins have been looked at, whether these should be cylindrical or oval in shape, right? So many things have been looked at in this. Okay, but overall this kind of configuration is able to provide more heat transfer for a given pressure drop when compared to microchannel configuration. The disadvantage is that this is a bit more difficult to fabricate at the small scale. Okay, fine. Sorry. So by pressure drop I mean flow is flowing from this end to this end. What is the pressure drop required to make the flow to flow through this array of pin fins? नहीं, वो cavitation तक नहीं जा रहे हैं, ये we are far away from cavitation. Yeah, so that is not a concern here. Yeah, so we are well above the vapor pressure, so that does not happen. Any other question? Okay, so this was a brief overview of single phase cooling. Now coming to phase change cooling. Okay, so if we let the fluid change its phase, then the fluid can absorb latent heat, and so we can deal with higher heat fluxes also. So in phase change cooling, one of the devices that has been used a lot both for cooling of microprocessors and also being explored for thermal management of batteries is a heat pipe. Many of you would have already read about this in your undergrad heat transfer. So a heat pipe is basically a device to transfer phase change based heat from a heat source to heat sink. So what you have here is three zones: evaporator section, adiabatic section and condenser section. So this evaporator section is in contact with your heat dissipating device, and this condenser section is in contact with your heat sink that ejects the heat to the outer atmosphere. So there is a wick, and in this wick the liquid coolant flows through capillary pumping. I will briefly explain how this works. So this wick absorbs heat from the outer body, the liquid evaporates, it goes into this central vapor section, and the vapor flows towards the condenser section where it condenses back into the wick and the liquid coolant comes back. So there is no active pumping involved, but it is the capillary effect that passively pumps the liquid from the condenser section to the evaporator section. Okay. So this device is also not new, right? It was invented way back in the 1960s, right? But nowadays most of your laptops that you are using, they all have heat pipes of different configurations. Okay. And in the heat pipe, the working fluid can be selected based on the application, right? Many times it is just water, but it can also be some alcohol, right, depending upon the temperature range that we are looking at. And usually the space inside the heat pipe is evacuated. We remove all the non-condensable gases, and it is only the coolant and its vapors as far as possible. Okay, because any non-condensable gases inside the heat pipe will severely reduce the heat transfer efficiency. Okay, and in the wick, when we have to design the wick, there are few parameters that we take care of. One is the pore radius. Pore radius means the size of the individual pore of the wick that decides how much capillary pumping is available for pumping of the liquid. Then the permeability of the wick, that governs that if the liquid has to flow through the wick, how much pressure drop it will experience. And then of course the thermal conductivity of the wick material. So we don't want the wick material to be made of something that is insulating, that will defeat the purpose. So it has to be made of a high thermal conductivity material. But in general, compromises are made in these three parameters to maximize the overall performance. Okay. So heat pipes can have different geometries, different kinds of wicks depending upon the application. Okay. Now there is one important aspect of heat pipes is that, let's say I have mounted the heat pipe in my laptop. Okay. In general it is working, but now you start playing some game or start doing some heavy computational simulation. The processor would work at a higher power, it will dissipate more heat, and the heat pipe has to transfer that heat from the evaporator to the condenser section. So is there a limit to which the heat pipe will work? So what do I mean by the limit? So let's say this is the heat pipe, this is the evaporator section. Can it happen that the liquid is coming back, but it is not able to come back at the same rate at which it is evaporating from the wick in the evaporator section? So if that happens, what will be the result? Here the wick will become devoid of the liquid coolant and the wick will dry up, and this is called as the dry out failure of the heat pipe. And then in that case latent heat absorption will not be available to you, and only conduction through the heat pipe body will be available, right, and that will lead to a rise in the temperature of the device that you are trying to cool. Okay. So there are different limits to the operation of the heat pipe that have been looked at. Okay. So the first and the most important limit is the capillary limit on heat pipe. So let me briefly explain this here. So let us consider the wick. Let's say it consists of these different microstructures. I am drawing just a 3D sketch. Now if I look it from the side, it will look like this. Okay. And let us say some liquid has wet this wick. So the liquid will form meniscus in this wick like this. Okay. And say now heat is coming from below. Now what will happen? This liquid will absorb this heat and it will start to evaporate. Okay. So liquid is evaporating, but it is also flowing along the wick. Okay. So it is flowing in this direction through these array of channels of pillars. Okay. So the result will be that towards the far end of this wick, the curvature of the meniscus will be high, and at the upstream end the curvature will be low. Okay. So what does this mean? If we recall Laplace pressure, so Laplace pressure difference is for any spherical curvature is 2 sigma by r, where r is the radius of curvature, and here the radius of curvature is small, here the radius of curvature is large, right. So this means that here the liquid pressure PL, let us say this is 2, this is PL1. So PL2 is less than PL1, right, and so there is a pressure gradient, and so this pressure gradient is going to drive the liquid flow in this direction, and this is called as your capillary pumping pressure, whatever that net pressure difference is. Okay. Now capillary pumping pressure, the job of the capillary pumping pressure is to suck the liquid through the wick from the condenser end to the evaporator end. Okay, and that is the maximum driving force that is available for the flow, for the working of the heat pipe. Now this capillary pumping pressure delta Pc, it has to work against 3 pressure drops. First is the pressure drop of the liquid as it flows through the wick, then the pressure drop of the vapor as it flows through the center section, and then any gravity related pressure drop if the depending upon the orientation of the heat pipe, if the heat pipe is large in dimensions. Now the heat pipe will work properly, that is the wick will not dry out at the evaporator section as long as the capillary pumping pressure is greater than the sum of these 3. Okay. Now as I keep on inputting more and more heat, delta PL will keep on increasing because the liquid flow is increasing. Okay. And eventually what will happen is that this sum will become larger than this, and so at that point the liquid will not be able to compensate for the evaporation and the wick will dry out, and this is called as the capillary limit on heat pipe operation. So any heat pipe that is being used for thermal management of microprocessor or any battery pack, a capillary limit will be specified, that is beyond which the heat pipe will not work, its wick will dry out. Okay. So this is the most important limit on heat pipe operation. but there are some few other limits that have also been identified, which can sometimes manifest based upon the design of the heat pipe. For example, there is a boiling limit on heat pipe operation, right? So let's say I have a wick of the heat pipe, and at some location boiling starts, right? So what will happen? Some bubbles will start to form. Now in conventional pool boiling, the bubbles can come out of the liquid, but here the bubbles can get trapped in the wick, and those bubbles can then block the flow of the liquid, and that is called as the boiling limit. So if this also happens, then again the wick will dry out, okay, sufficient liquid will not be able to reach, right? And then there are also a few other limits like sonic limit, that is how fast the vapor can flow. The maximum speed at which the vapor can flow is the speed of sound, right? Similarly, there are few other limits which I will not go into the detail, but what essentially I want to say here is that these limits, at what operating temperature these limits arise, that depends upon the design of the heat pipe. Usually the capillary limit is the first to reach, and so that is why it is the most commonly talked about, but in certain situations other limits can occur, and then the designer of the heat pipe has to be careful about when, at what operating temperature these limits will be reached, because any such limit will diminish the performance of the heat pipe. Okay. Okay. So now, in case of large static systems like your desktop or servers, you will not require these heat pipes. They are mainly for mobile devices, right? So for example, here this is a schematic of how the heat flux dissipation in smartphones has increased over the years, right? But at the same time, the thickness of the smartphone has reduced, right? So right now the thickness has seemed to be stabilized, but 6-7 years back there was a lot of competition between different OEMs and how much thin I can make the phone and how fast the phone is. Now this is a dual challenge for a thermal engineer. You have lesser and lesser space available to dissipate more and more heat, right? So there then comes how to design such very thin heat pipes that can operate in such small space. So here you have different configurations of the very thin heat pipes being implemented in laptops, in smartphones, in smartwatches. Okay, and overall, as a thumb rule, if you see in the literature, the heat dissipation of the processor in a laptop is around 20 watts, and that in the case of a smartphone is around 5 watts. Now the processor designers are trying to bring this down even further, but whatever that is, heat is, that has to be dissipated. So here we come across another counterpart of the heat pipe. It's called as the vapor chamber. So vapor chamber is same as the heat pipe. The only difference is that in the heat pipe, the evaporator and the condenser were separated by a certain distance. In the case of vapor chamber, the evaporator and the condenser are directly facing each other, and this vapor chamber can then dissipate heat in the z direction. And in some of the smartphones now, this configuration of the vapor chambers is being implemented. Here it is showing how thin a vapor chamber can be. About, I think, 2-3 years back, Samsung had advertised that okay, the phones are liquid cooled. Now there the liquid cooling was referring to the introduction of the vapor chamber in the heat pipe. So what the vapor chamber is doing is that in the smartphone, the processor is occupying a small area. The job of the vapor chamber is to spread that heat over the larger area so that it can be dissipated through the back surface of the smartphone to the outer atmosphere, thus maintaining the processor in its safe operating limit. And inside this vapor chamber. On one surface you will have the evaporator, and on the opposing surface you have the condenser with its own wick architecture. Okay. So here is just a picture of realistic heat pipes, how they are being implemented in the laptops. For example, here you have the two evaporator sections, and then here this is connected to a condenser and then to the heat sink, because in the laptop, the, let's say your processor is somewhere here, right, but the fan is somewhere here. So then the job of the heat pipe would be to carry the heat from here to the heat sink that is connected to the fan. Okay. So there are many existing challenges in ultra thin heat pipes. Okay. So the one of the really interesting and yet unsolved challenges, how to make flexible ultra thin heat pipes. So you would have heard this word of flexible electronics, right? Very thin smartwatches, right? So for that, and also in biomedical applications, Internet of Things, you need flexible electronics. So can we, or do we need certain very thin heat pipes or vapor chambers which are also flexible? But for flexibility, you need to use polymeric materials, but polymers have low thermal conductivity. So work needs to be done to design new materials for these kinds of applications, right, where flexible heat pipes or vapor chambers can be developed. And this is a prime example of interdisciplinarity, where material science, fluid mechanics, heat transfer, they have to come together to design new working devices. Okay. Then I like to briefly talk about thin film evaporation. So this is fundamental to the working of all heat pipes and vapor chambers. So if we look closely, let's say if we focus on this region, okay, so this picture is a zoomed in image of this, where this part, so this is zoomed in and rotated 90 degree. Okay. So here is the solid surface and there is the liquid film being formed. Now here there are three regions of the film thickness. Region 1 has the smallest film thickness, region 2 is intermediate, region 3 is large. In region 1, the film thickness is so small that the liquid molecules are strongly adsorbed to the solid surface. Okay. And what happens is that here the adhesion force is so high that whatever the heat flux is, these liquid molecules will not separate and enter into the vapor phase. So here if I try to calculate the thermal resistance will be infinite. On this side, this adhesion force is small, but due to the large thickness of the liquid, you have large conduction resistance. So again here the thermal resistance is high. It is this region 2 that is the sweet spot, where the thermal resistance is small and the heat flux is high. So when we are designing any wick, new wick for heat pipes or vapor chambers, the target is to maximize this region per unit area of the device. So if this region is large, you can get high heat transfer coefficient. So this is called as the thin film region. So you want the thin film region per unit area of the device to be as large as possible. Okay. And that is done through micro and nano texturing. So either you make separate wicks or you micro or nano texture the surface of the various so for example here you have the nano texture. Okay. So what we see here is these are the holes. If you see the scale, the whole scale is very small. Okay. So different kind of textures can be made to try to maximize that thin film region that I was mentioning. So many research groups are working on this problem to develop new scale textures either at the micro scale or the nanoscale. For example, here, went one. Like here you see, you have a micro scale, you have 20 micron texture, and on top of that you have a nano texture. Okay, so dual scale texture where it is being tried to maximize the thin film area and increase the heat transfer coefficient. Okay. Now, this was one kind of phase change. So, phase change for water, it can be either in the form of evaporation or the other can be boiling, right. So, what is the difference between evaporation and boiling? Can somebody tell me?
Rate of change of temperature
No, what is the physical difference in the process between evaporation and boiling? So, evaporation is at the surface of the liquid air interface, boiling is at this liquid solid interface, right. So, boiling, in boiling you can achieve much higher heat flux, right. So, instead of evaporation, a lot of work has also gone into flow boiling. So, let us say I was talking about single phase cooling where liquid is flowing in the channel. How about that as it flows through, it also undergoes boiling, then you can absorb much higher heat flux, right. But if we all know this, but it has not yet been commercially implemented. So, what are the bottlenecks there? The main issue is how the nature of flow changes in the downstream direction. So, here if you see the flow is entering, it is single phase flow, the boiling starts, okay, and then you have annular flow and eventually the liquid layer next to the wall dries out and you have a mist flow. Now, as thermal engineer, I would like to remain in this zone, but it is not so trivial to maintain the flow, the nature of flow like this, because the nature of flow is heavily dependent upon the flow rate and the overall pressure drop, right. And so, a lot of control algorithms are implemented usually while dealing with flow boiling, where continuously the flow rate, the temperatures are controlled so that the flow remains in the preferred region and maintains the wetness of the walls. Okay. There can be many instabilities in this flow. For example, here liquid is coming, it is entering into these channels, boiling is happening, but perhaps when the boiling happens, the vapor starts to get accumulated near the inlet zone and it chokes the flow. The liquid is not able to enter the microchannels and eventually here you have a dry out. So, flow boiling is very promising, but these bottlenecks need to be overcome. Okay. And then further, if you want to increase heat transfer, you can mix both the strategies in the form of a jet. So, two-phase jet impingement, where jet is impinging on the hot surface and it is also undergoing phase change. So, there you get the benefit of both the flow field of the impinging jet as well as the latent heat absorption due to boiling. But again here the challenge is how to control this phenomena so that the net overall flow always remains within our preferred type. Okay, so I will close this lecture by a short discussion on battery thermal management in EVs, the electric vehicles. Okay, so in electric vehicles, the batteries all need to be maintained right within the required temperature zone. So various strategies are being used, and the strategies that I have mentioned, all of them or a combination of these are being tried. For example, single phase cooling, you can have air cooling that is going through the battery packs. Okay, then you can have liquid cooling. So here you have the battery cells, and either these battery cells can be directly immersed in cooling oil which is dielectric, or you can circulate water, you can have indirect cooling. So this is a schematic from one of the patents filed by Tesla many years back, and they have made this patent public. Okay, so you have here this cooling channels where liquid coolant is being used to cool the battery pack, and then other strategies can be used. For example, cabin air can be circulated through the battery pack. You can have your air conditioning system, part of which can be used for phase change cooling, where the refrigerant is circulated through the pack. You can also have a combination of heat pipes in conjunction with single phase cooling, where heat pipes, if you have the battery pack, so from within the pack, the job of the heat pipe is to transfer the heat out, from where it is then carried away by the coolant, right? You can also utilize phase change materials, where like where the any spike in the heat flux would be managed, right? So different strategies in different combinations have been utilized. So I think I'll stop here. Yeah, it's 12:31. Okay. If any questions? Yeah.
And does the working temperature for the heat pipe depend on the laser fluid which is used in it, or heat pipes are designed for different working temperatures?
So the working temperature of the heat pipe will depend upon the working fluid and at what pressure it is charged in the heat pipe. So for example, water, its boiling temperature is 100 degrees C, but if depending upon the pressure at which water is charged, I can achieve different working temperatures, because I am changing the saturation pressure, so then the saturation temperature is also changing at the same time. Okay. So for example, if you have a pressure of around a few tens of millibars, then the saturation temperature can be brought down to 30-40 degrees or even lower also. So it all depends upon which working fluid and at what pressure it is charged in the heat pipe. Okay. Any other question? Uh, I'll need to check that. I'm not sure if it has been implemented yet. Maybe Ankur can answer. Yeah.
Certainly, at the scale of academic research, this is something that we will
Mm.
I don't think it is a product.
Mm. Yeah. Okay. Any other question? Okay.
Also, I know I'm present between everyone and the lab. That the amount of fluid that we get, because we said that the pressure remains that particular temperature at which the phase change takes place of the fluid inside the heat pipe.
Yes.
The quantity of fluid inside the heat pipe, does that matter when you are taking it?
Yes, it does. So the dry out heat flux will also depend upon how much fluid is there inside, and that is why whenever new heat pipe is designed, it is tested at different charging ratio. So charging ratio means the amount of the liquid added divided by the internal volume of the heat pipe. So that is also strongly a parameter.
Is it like well-known values are available, or it depends on any type of design and lot of
It is dependent upon the design also. Yeah. Generic values are not. There are a lot of values available in different academic papers, but as such general thumb rules are not.
super complicated 3-4 hours.
Yes, 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 yes. Yeah. Okay. Thank you. Okay.
let's get started. This is lecture number 12 of our GIAN course on heat transfer in lithium batteries and electrochemical energy storage systems. We have been learning a lot about heat transfer, like mathematics, measurements, etc. Right? And I've been summarizing the research field in that area. I'm going to take a small detour in this lecture and talk about technical communication. So the idea here is that after doing all the hard work that we do, right, take some difficult measurements, solve some difficult theoretical problems, etc. After all that, we need to communicate the results to the rest of the world. If you don't communicate the results to the rest of the world, what would have been the point of having done all that research, right? And therefore, it is very important for all of us, in addition to being good researchers, to also be good communicators. And that is what I will focus on in this seminar. I want all of you, each one of you, to be able to present your research very well in an oral fashion, like stand up in front of an audience and talk about your work, and in a written fashion, meaning write the results of your research in an effective manner that others read and appreciate and benefit. Okay? So in the next 1.5 hours, I will focus on both oral communication and written communication. I will share with you some tips and tricks that I have learned myself over the years about becoming a confident speaker and becoming an effective technical writer. Okay? I am convinced, absolutely convinced, that this is an extremely important skill to have in addition to doing good research. So if you are in the PhD program, in addition to learning new technical skills, you should also be learning and becoming a better public speaker, a better written communicator, and so on and so forth. Okay, this is before you hit the real world and go out there. This in school is a great opportunity for you to get better at public speaking and at writing. And today, through some slides that I have built over the last several years, I will share some tips and tricks about being a good technical communicator. Okay, so we'll begin with talking about effective presentations. So the idea here is, how do we give effective presentations? And somebody would have to tell me how this goes. Oh, okay. So I'll skip this. So the question is, why do you want to give a presentation? When you are preparing to give a presentation, I want you to think about, why are you there in the situation of giving a presentation? Who is your audience? What is the forum? And what is the intention for the audience to spend time with you? You all are here. There must have been a reason why you are here, right? When I decide how I want to present, I need to think about that. I need to think about what is the motivation of the audience for giving this presentation. And of course, also, what is my own goal in giving the presentation? What am I trying to get out of this interaction between you and me? And I need to try and drive towards getting you that benefit that you're looking for, and getting myself the benefit that I am looking for. My slides, my way of speaking, the technical content of the presentation, etc., should all be geared keeping all of this in mind. Okay? Note that giving presentations is a part and parcel of your professional lives. One day you will graduate, go work for a company, or become a professor yourself. No matter what you do, throughout your lives, you will probably be giving presentations all the time. This is something that you will never be able to leave behind. In 5 years, you may be working on an entirely different research area, but you will still be presenting it. You'll present it to your colleagues, to your boss, to the CEO of the company, to your customers, to your vendors. No matter who the audience is, you will never get away from presenting, right? And if it is something that important, and if it is going to determine your professional growth, then you better get good at it. There is no doubt that your professional growth will be determined by the quality of your presentations. You will be judged very soon as you give your defense. You will be judged by the quality of your presentations. No one in the committee is going to go to the lab and take a look at your experimental setup, right? They will look at the picture that you showed there. And therefore, the quality of that picture should be representative of the actual quality of the work that you've done in the lab. You've worked many months to set up a very beautiful experimental setup if you don't take a nice picture of it, and if it is that poor shabby picture that shows up in your presentation, then that becomes representative of your work, not the actual work that you've done. You know what I'm saying? So you have to put almost as much effort in designing your presentation as the effort that you have put in doing the work. Okay, it deserves that. And if there is one thing that I want you to take away from our interactions here, it is that practice is the most important ingredient of becoming a good presenter. If you practice enough number of times, you can present to any audience. Even the most experienced people often feel nervous before giving an important presentation. It is natural to feel nervous, especially if it is an important presentation, right? If I am giving a presentation for my PhD defense, then it is natural to feel a little fluttery, some butterflies in your stomach. It's okay. Take a deep breath. If you have practiced your defense talk 5 times in front of an appreciative audience, then you will certainly do well. Okay? So the number one thing to remember from everything you're listening to here is the importance of practice. When I was a student many years ago, I used to feel very, very shivery and uneasy, and I just wanted to run away from any opportunity to present and so on. It comes with practice. I have now given this talk and my other talks enough number of times that I feel confident about it. But I was not like that when I started. All right? I don't think there is anybody who's born with the innate skill of presenting. And even if you're not born with it, it's okay. You can get it. You can learn, right? It's like walking. Nobody knew how to walk when they were born. We all learn it, and then we start running, and then somebody runs a marathon and becomes an extremely good runner. That person didn't run a marathon as soon as he came into this world, right? Similarly, all these good presenters you see all around on the internet, whatever, they got there by practicing, and so can you, is all I'm saying. Okay? One more thing that I want to share with you all is that as a student, as a technical scientist, engineer, etc., you've got to be able to give a 60-minute talk, a 20-minute talk, and a 2-minute talk as well. Right? So, say one of you is walking with me back to lunch, and I ask you, what research do you do? You have only about 2 minutes to spend on somebody, and in those 2 minutes, you have to be able to summarize what work you're doing. Oftentimes, giving a 2-minute talk is much more difficult than giving a 60-minute talk, because you've got to really summarize a lot of things in a very short amount of time. You will, I'm quite confident, see those occasions when you've got to really just put it out, sort of like TikTok, right? You've got, what, 15 seconds or whatever it is, in which you have to summarize a lot of things. Okay? So be ready to do that as you progress in your careers. I want to say a few things about virtual presentations, because that has become a part and parcel of our professional lives. Before COVID, I didn't have this slide, but it turns out that virtual presentations are now a way of life. Even very important things like job interviews, a dissertation defense, etc., now happen on virtual tools. So it's important for yourself to familiarize with the virtual tool. How many of you have used Zoom? Most. Teams, it's also very common, but those are not the only two ones. There is this thing called GoToWebinar, and there are at least a few others. And when somebody sends me an invite with this weird tool that I have never used, I have to be ready to expect any surprises, right? My computer can restart at any time to install some random update, right? All kinds of things can go wrong when doing a virtual presentation. If the occasion is important enough, you've got to be prepared, right? Make sure you switch on and switch off your computer once so that it installs whatever stupid updates it needs to install. Install the software tool directly. Have a backup device. Make sure your equipment works. Make sure you're well dressed, right? From the top to the bottom, by the way, not just the top, right? And give a virtual practice talk in advance. Using the same tool, using the same setup, have a couple of your friends join virtually and listen to you and give you feedback about whether they were able to hear you, they were able to see you, whether everything worked well or not. right? Prepare in advance. And when you are giving your presentation, make sure that you keep gauging audience engagement by asking questions. Am I clear? Can you still hear me? Do I need to say something else, etc., etc.? That keeps the audience engaged in your presentation. And keep in mind that just because it is virtual does not mean that it is not important. As I said, these days, even very important things, meetings, presentations, etc., happen online. Okay? So, what I will do in the rest of this part of my talk is to talk a few things about how to present, right? How to approach the thought of giving a presentation, and I will also give a few practical talks, practical suggestions about the PowerPoint presentation that you will probably make in order to present. Okay. And by the way, I'm happy to share these slides with anyone. So if you would like, this is Pesky. If you would like, I'll be happy to share these slides with you. Okay. First of all, the first question in organizing your talk is how many slides should I have? And the approximate answer to that is about 2 minutes per slide should be your budget. If you have a 60-minute presentation, don't have 100 slides. That's unfair. Your audience will simply not be able to understand 100 slides in 60 minutes, especially if you're presenting some dense work, right? You've got to give yourself enough time to be able to teach the audience what you're trying to teach them. It's better to teach them less but effectively rather than throw a bunch of material at them and not explain what in the world is going on. So what I try to do is about 2 minutes per slide, and I feel that having too many slides is worse than having few. If I have fewer slides, I have more time to spend on it. But if I throw 200 slides into my deck, I will never be able to tell everything. Okay? The title slide is very important because people look at it for a long time. So make sure you have a nice clear title on the title slide. Make sure you have a nice picture of your research on the title slide, your affiliation, etc., etc. The title slide should look professional. I say this to my students, of course this changes. Use your institutional logo. Why not throw the logo of your institution on the bottom and make it look nice, professional, right? Heavy. You want to create a good solid impression. In other words, your for the men here, it should look like you're wearing a tie and not coming in kurta pajama if it is an important presentation. You've got to spend sufficient time in the introductory slides. I like to say, and somebody said this to me, that your grandmother should be able to understand the first 2 slides of your presentation. After that, if you lose her attention, it's okay. But the first 2 slides, she should be able to understand what in the world is going on, right? So the first 2 slides should be a big picture overview of the entire field in which your work is there. Answer a few questions. Why is this work important? What is the big picture of the importance of this work? How will this work save the world, right? And the second question you should answer is, why should the audience be interested? Try to somehow connect your work with the audience. Make them part of this discussion, right? Think of an example which people will be able to relate to, right? So for example, when I give talks about battery heat transfer, I often talk about cell phones and how cell phones get hot, because that is something most people have experienced, right? And that way I try to make a connection with the rest of the audience. Keep also in mind that first impression is the last impression. Most people will have judged your talk within the first 5 minutes of the presentation. Beyond that, they are just listening and, there's minor adjustment in their assessment of your work. It's the first 5 minutes that are extremely important for you to win or lose your audience. And of course, I'm not saying spoon feed everything to the audience. After the first few slides, if your content becomes more and more complicated, that's okay. In fact, the last 2 slides should be pretty difficult to understand, because you also want to give an impression about the difficulty of your work, right? You're not teaching ABCD here. It's okay to teach ABCD for the first couple of slides, but towards the last slide, you've got to get up to Shakespeare or something like that. Yeah? On the other end of the talk, concluding your talk appropriately is also important. So at the end, you must re-emphasize the important things that came out of your talk. Think in advance about 2 or 3 most important things that you want the audience to remember, to take away with them. And those 2 and 3 things you should restate towards the end of your talk. Right? And then in the end, thank the audience and ask for questions. Perhaps the last slide should just have 2 sentences that conclude everything that you want the audience to remember even 2 days, 3 days after your talk. Okay? Keep in mind that you are very familiar with the material, but the audience is not. The audience needs a little extra time to understand what you're talking about. And that is why putting those things explicitly in your last slide helps the audience understand it better. Okay? Any questions or comments so far? Yes. Sure, the logo can be wherever you would like it to be. Just keep it consistent. Okay? All right. In general, confidence is the most important thing. Okay, you've got to stand up confidently. Everything about the presentation needs to show confidence. The quality of your slides, your body language, the way you're dressed up, and everything else. You've got to show your enthusiasm should be flowing out of you through your body language. Right? So one thing that people say is that you should smile. Right? If you don't smile, people think that you're not interested. Right? Whereas if you're enthusiastic, you're smiling, it shows that you are invested in the work, that you're enthusiastic about it, you're passionate about it. Okay? The way you look at everyone in the audience makes a very big difference. So for an audience of about 20 people like this, I try to look at each one of you eye to eye within this 30-40 minutes of my presentation. Okay? That eye contact is very important, I feel. Alright? Certainly do not speak like this. Certainly don't look at the floor or the ceiling or at your slides all the time. This happens all the time. I see people who give a presentation like this. Right? The audience is not there to see your back. The audience is there to see your face and to talk with you. Right? The slides are just a facilitator to have a conversation with the audience. And if all that you are going to do is to read the slides, then what is the point of having a meeting? Then I could just email the slides to everyone and everyone could just read the slides wherever they are. The audience didn't come here to read your slides. The audience came here to hear you. And the audience should not be forced to listen to you reading material that is already there. Right? The audience knows how to read. You don't have to read it to them, is what I'm saying. Okay? Face the audience and address them. Don't just keep looking at the slides. Someone told me that it shows a lot of confidence to move your hands quite a lot when you talk. So instead of this is very confrontational. Right? I'm almost saying, do you have any problem with me? Right? When I do that. Instead, when I do this, I feel like I'm opening myself to you and your ideas. So use these skills, these technical ideas about effective technical presentations. By the way, there's a whole organization called Toastmasters. Is there a Toastmasters chapter here on campus? So Toastmasters is an organization which is focused on public speaking, and they have chapters at different campuses, run essentially by students, and everybody in the Toastmasters organization is essentially interested in becoming a better public speaker. They meet once a week or whatever and have seminars and this that about public speaking. If there isn't one, take a look and see if any one of you is interested in starting one here at Ropar. Also keep in mind that most of the times you know about that topic more than anybody else in the audience. You are the expert, right? When you go on and do your PhD dissertation defense, nobody in that room, including your advisor, knows more about that topic than you do. You are the one who was there in the lab at 12 o'clock in the night and took those measurements or ran those simulations, right? That should give you confidence that you can give a good presentation. Another thing that should give you confidence is that most of the times the audience is not out there to make you feel bad or embarrassed, right? Most of the times nobody there genuinely wants to trip you or make you fail or to not see you succeed, right? We all are here because we are a community, right? A community of scholars and academicians, and we want everyone to succeed. And so feel, don't feel that people will throw eggs at me. They will not. They really want to listen to something from you. That's why they're here, and they really want me to succeed. Okay? And again, practice, practice, practice. The more you practice, the better you will get at it. Whenever I make new slides and I present it for the first time, I stumble. It doesn't come out well because I'm not very familiar with the slides. I don't know which is the next slide that will come after this. It's not in tune with me. But the second time I give that same presentation, I remember the places where I stumbled and I get a little better at it. The third time, the fourth time, the fifth time, I progressively get better. By about the fifth time I have given a presentation, I am much, much better than that first time. So the message is that if it is an important enough presentation, you should have given that presentation already several number of times. Don't finish making your slides for your dissertation one day before. Finish it 2 weeks before so that you can gather up your lab mates and ask them to listen to your presentation and give feedback, give good honest feedback. Okay, feed them pizza if that is what it takes. Get good critical feedback from them. Okay, it's a good idea to memorize the first and last few lines of your talk, and it's a good idea to time your slides. You should have some vague idea of which of these slides you will be able to go through very quickly and which of these slides you will be able to, which will take time for you to do. For example, I know that I have about 18 slides in this presentation, and if I am at slide number 9, I am at the midway point, and I can calibrate looking at the clock. I can either speed up or slow down in order to finish the last half of the talk. This happens very commonly that you have only 2 minutes left in your talk, in your allocated time, but there are 20 slides remaining. Don't get into that situation because that situation becomes very embarrassing. So know your halfway point and make an adjustment much in advance. Don't wait for the last 2 minutes. Make this adjustment much in advance. You'll be able to adjust much more smoothly and comfortably. You shouldn't become an express train only in the last 2 minutes in order to finish. Okay? Speak loudly, clearly, and slowly. So speaking loudly and slowly is often problematic because when we speak loudly, we tend to speak fast as well. But what I am asking you to do is to speak slower but louder, and that takes a little bit of practice. Why do you want to do that? Because you want to give the audience a little extra time to understand the material that you're teaching or communicating, right? The audience needs a little extra time to be able to understand what you're saying. So if you speak at the same speed as if you're having a regular hallway conversation, that's too fast for people to understand what you're saying. So go a little slower than that and go a little louder than usual so that people can easily hear you and understand what in the world is going on. Okay, so slower than a regular conversation. And it's important to communicate the message rather than speak good English. Even if you are not a good English speaker, that's okay. That's not what the audience will evaluate you on the basis of. You can always use very plain English, very simple sentence structures, and still be able to communicate the technical points that are important, right? It's the engineering or the science you're doing which is important and not the language. In our community, science and engineering, it's important to be precise. Those who give a dissertation defense in English probably keep speaking forever and go here and go there and meander around. We don't do that. We have a technical, a scientific message to convey, and for that our language needs to be precise and to the point. It's helpful to move around the room a little bit, but not too much, and please plan your timing very well. As I said, panicking in the last 1 or 2 minutes looks very unprofessional. Okay? Any questions or comments so far? How do I go back? Okay, now I think you can. Okay. So now what I will do is that I will talk about some practical suggestions related to PowerPoint. Almost all of us use PowerPoint. Is there anybody here who does not use PowerPoint for their slides? I know some weird people who use LaTeX to make PowerPoint presentations. Good luck to them. But I stick to PowerPoint. 99.9% of the world sticks to PowerPoint. And so here are a few suggestions about PowerPoint, right? And I want to communicate these suggestions by showing an example, a good example of a bad slide. This is a poor slide. Why is it a poor slide? Too much information. Exactly. This slide has too much information. Perhaps if I had done all this work, I would be very familiar with all of this. I will know what is going on. But the audience does not know this. Even your advisor, even your committee members probably do not understand all of this as much as you do. Right? I hope you worked hard enough to get to that stage. At that point, if you show them all of this, if you throw all of this at them, not much will stick. It is your job to break it down into easily digestible nuggets and present one nugget at a time. Okay? So your slides need to be very well designed. They need to be a pleasure to look at. Somebody looks at it and says, yeah, that looks beautiful, and I think it makes a lot of sense. And not, oh God, I don't know what this is. I can't even read all this. Right? In 2 minutes time, it is impossible for someone sitting in the back to read all of that and then to also understand everything that is being said. That is beyond most human beings. How do I make good plots? This is very important. Plots are the heart of our presentations. No matter what we do, we all will make some kind of a plot, right? The quality of that plot determines the quality of the presentation. All right? So you must have spent a lot of time in making good quality plots. I tell my students, the quality of the plots is non-negotiable. I am not going to negotiate on it. If the plots do not have good quality, we are not moving forward no matter what happens. Go back please and make sure that the plots are the best possible quality. So here is a good example of a good plot and a bad plot. Can somebody tell me a couple of good things about the one on the left? It's very clear, right? That one is grainy, a little hazy, the line is kind of jagged. This one, everything is nice and smooth. What else do you like about the left plot? Sorry? Readability, exactly. See, the font sizes are large enough for me to be able to read. Oftentimes what happens is that when you make a plot in MATLAB or something like that, the legend font is smaller. And when it is in front of you on the screen, it looks okay. But then you put the same plot on PowerPoint and project it to an audience in a large room. Then from the back, this font becomes very difficult to read. That is why you have to go to the PowerPoint, you have to go to the MATLAB fig file and you have to increase the font size of the inset, so that this font size is almost the same as the rest of the fonts. Okay, I've used 5 different colors and 4 different line styles, right? I've tried to break the monotony. If this was a black and white plot, it would have been difficult to read and understand, right? But I have tried to use multiple different colors and colors and line styles in order to be able to make the point I'm trying to make. Okay. Finally, this is accompanied by a very detailed title or caption for the plot. Right? This caption tells me almost everything that I need to know about this plot. Whereas this says temperature versus time plot. Oh, what in the world does that mean? Temperature of what or temperature of who? Right? This is the time not to be short. This is the time to define your figure as well as you possibly can. Okay. Never make your plots in Excel. Okay. If you're still using Excel to make your plots, please grow up and start using a more professional tool such as MATLAB. Okay. These are examples of plots made in Excel. I can almost see a plot and say that look, this was made in Excel. It's poor, very, very poor. Minimize the amount of data in plots. Your plots should not be a jumbo mumbo of data like it is shown here. Right? It's very difficult for people to untangle this and understand what in the world is going on. Simplify things. Have multiple plots if needed. Increase the font size of the plots yourself. Don't depend on the default that MATLAB gives you. Right? Nobody knows why MATLAB gives you the default font size. I always increase that font size a little bit just for things to look nice and happy. Okay? Keep in mind that maybe you can understand all this because you were the one that took the measurements, but not the audience. So give them the ability to understand things by simplifying it for them a little bit. Never show raw data. There is no point of presenting raw data. Nobody can understand this data the way it is written. You can always plot it. Okay? At the minimum, use 16-point font size. More commonly, my recommendation is to use at least 18. Okay? And when it comes to font type, it is very well known that the correct font to use in presentations is Arial and not Times New Roman. Times New Roman is known to be a good font for written reports, but for presentations, Arial is the right one. Apart from these, don't use any other fancy fonts. Never use yellow, avoid orange, and never use all caps. And finally, your slides should have 0 spelling mistakes or grammatical errors. Maybe one. One is allowed. When I am the audience and I look at a presentation and I see one spelling mistake, I take a deep breath, control myself, and give the benefit of the doubt to the speaker. I say, okay, it's okay. But if I see a second spelling mistake, I completely switch myself off and start doing anything else that I need to do. Okay? Do what it takes to find and eliminate all spelling mistakes and grammatical errors in your slides. Give it to somebody else and say, you know, I'll cook dinner for you, or I'll take you out, or whatever it takes. Please, can you look at my slides and help me fix all mistakes that there may be in the slides. Okay? Don't use animations. This little animation that happened, it came down from the bottom and settled down there. Actually, PowerPoint can do even more funny things. Something can come here and fly around and then come here. We're not trying to make it dramatic. And the audience is not 5-year-old kids who want that kind of thrill, right? Our job is very simple. Our job is to come here, communicate a few ideas, and let the audience go away with some points, right? Anything else that you do distracts the audience from that transfer of information, right? So keep things simple. I am a big fan of minimalism. See, I didn't have a lot of people, use these PowerPoint templates in which half the slide is covered by some sort of background and all that stuff, which doesn't even make sense. Don't use that. A plain white slide, maybe with a red or blue or some such boundary, is just enough for your needs. Okay? People in sales and marketing may be okay, but engineering, technical work, science, we need to be minimalistic. I do not like to have an outline slide in my work, in my presentations, but if you think it is helpful for yours, that's okay. Certainly keep it. Okay? Keep in mind that a lot of the things I am saying is not universal truth. I am saying do not have an outline slide. You could very well say, no, I think it is helpful based on my style to have an outline slide. And if that is the case, then yeah, have an outline slide, right? This is not God's word. This is not Newton's law of presentations, which has to be correct and true and to be followed all the time. All I want you to do is to think carefully about your presentations and design your presentations. Your presentations should not just randomly come together on the last minute. You should have thought about it enough, you should have designed it, you should have iterated upon it, and that is when it should have come together as a beautiful final product, is what I'm trying to say here. Okay? Having figures is a good idea. So unless you're doing extreme mathematical work, it's a good idea to have at least one picture, figure, plot, something like that per slide, just to break the monotony. Okay? And when you do that, it is important for you to acknowledge all figures, especially those that are not from your work. So if you borrowed this figure from somebody else, you just write their name and the year or something like that in order to convey clearly that, look, I'm not trying to pass that off as my own work. Box your figures. I feel like putting a box around the figure makes it look better, and of course box the entire slide. That also I find is helpful. Minimize text. As you can see, minimize text. If you can say something in 5 words instead of 10 words, do that. Okay? You don't have to write full sentences in your slides, and you don't have to write everything that the audience needs to know. The slides are just a means to an end. They are just a facilitator. It's not a report, right? A report and a presentation are different. A report is supposed to be comprehensive. It's supposed to have everything, right? But a presentation, just bullet points is sufficient. Okay? Give generous space between lines and don't just stand there and read your slides. That comes out very poorly. It shows extreme lack of confidence. And if you have to take a gulp of water once in a while, do that. It gives a very good break to yourself and to the audience as well, right? Nobody wants you to keep speaking for an hour without getting water if you need to. Handling questions and answers is also a very important part of giving presentations, because oftentimes people use that to gauge whether you know the material, whether you understand the material or not, etc., etc. So I will share some tips about running a good question and answer session at the end of your talk. Here's a few options. Firstly, you could specify Q&A policy in advance. A lot of the times, as a speaker, I could get rattled if people start asking me questions from the very start, right? And I have seen that happen, where there's a couple of people in the audience who are ready to jump and pounce on you almost as soon as you start, right? If you have such a person, and if you want to avoid that, you can politely specify the Q&A policy in advance. You can say at the very start that I will be very happy. I'm planning to speak only for 40 minutes. There'll be a lot of time towards the end. and I'll be happy to take questions at the end. All right. When you say that, that person might still anyway ask questions, but you've done your best, and that's okay. All right. You will find that there are all kinds of questions you will face. One category of questions is offensive questions, right? A 60-year-old professor gets up and says, that work was done by so and so in 1979. Why are you repeating this work? Right? It almost sounds like a personal insult, right? You have to take a deep breath, get some water if needed, and be polite in the response to that question, right? You cannot answer an offensive question with an offensive answer. You can't say you are too old, sit down, right? Or something like that. That's not. You have to somehow manage the situation. You have to say, I understand, Professor so and so, your concerns. I have also read that paper, and here are the reasons why my work is different from that paper's work, or something along those lines, right? On the other hand, there are also some questions which will sound, rather easy, or you feel like, what, you didn't understand even that much, right? Don't say that. Don't put it in such words. Do not ever consider a question to be stupid or foolish. If somebody has taken the courage to ask a question, he or she is really interested in understanding it. Why not help him or her by addressing that question very well, right? It's a sign that that person is actually interested in your work. In fact, if my 60-minute talk does not generate even a single question, it means I have completely failed at the task of communicating those ideas to the audience. I was not able to generate interest or enthusiasm in anybody enough to be able to ask a question, right? So getting good questions and getting a large number of questions is actually a good encouraging sign that your presentation went very well. Okay? So never be condescending. Never say, oh, I'm not even going to answer that question or something like that. Be polite and explain whatever needs to be explained to answer a simple question. Okay? And then another category of question that you will get is, somebody will get up and say, I have two questions for you. Question number one is blah, 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 blah. And question number two is blah, 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 blah. By the time they finish asking the two questions, you have forgotten the first question. Even they have forgotten the first question, right? People oftentimes are competing for time, right? And they want to throw out both questions at the same time so that they get answered, right? There are a few ways of addressing that. After that person has finished asking the two questions, you can take a deep breath and say, okay, those are two very good questions. Let us start by answering the second question, because you probably remember the second question, right? So answer the second question first and then say, oh, can you remind me what your first question was, right? And that way you've given yourself a little more time to remember, understand and calibrate and then answer your first question. Okay? Oftentimes it is helpful to repeat the question. Somebody asks you a question from the back, it's a long question, you need a little bit of time to think about it. In fact, the audience also needs time to understand that question. So if you say, oh, I think the question that you asked me was blah, 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 it gives you and it gives the audience some extra time to think about it and to frame your question properly. Okay? Oftentimes people will ask questions that are genuinely difficult to answer in the limited time that you have. And so you always have the nuclear option of saying, this is a complicated question because of the following reasons. Why don't we talk about it in the hallway after we are done with this seminar? You can use that maybe once in your Q&A. You can't say that for every question that comes your way. That will not look very good either. Okay? If you like a question, please acknowledge it. If somebody asks you a really insightful question, something that really goes to the heart of the problem that you are solving, that really helps you, that illuminates something in you, then hand on your heart, say it. Say, what a nice question. I really appreciate it. That brings us exactly to the point that I'm trying to make, and then answer the question. Okay? Again, remember, having lots of Q&A is actually a sign of a great presentation. So I think I'm coming to the end of this part of my talk. Miscellaneous things. make sure the technology works, the projector, the laptop, the laser pointer, the everything else, videos in particular. If you have videos in PowerPoint, oftentimes videos will work very well on your computer, and you connect it to the other computer, and suddenly you click click click, nothing happens, the video doesn't work, right? Figure out a foolproof way of handling your videos. I don't know the right answer to it. It's up to you. You have to figure out a way in which your videos will work for sure when you go to that room and give that presentation. Go to that room a day before and do a dress rehearsal exactly in that room to make sure everything is working. Okay? Shut down your cell phone, pop-up apps on your device, carry plenty of backup. I like to carry, if for important occasions, I like to carry my slides in my laptop, slides in my USB drive, slides on the cloud in PPT and PDF formats, so that if this doesn't work, that will work. If that doesn't even work, then there is like a double backup situation. I don't want to fail. I don't want to spend 5 minutes panicking trying to download something from somewhere. Internet nahi chal raha, ye ho raha hai, wo ho raha hai. That doesn't convey the right impression to people, right? You've got to look and sound professional. And carry a laser pointer and a spare battery for your work. Okay? So with that, I am finishing the first part of my talk, which was on oral communication. How do you stand up and give good presentations, which you all will do without any doubt throughout your professional careers. Okay, so I'll stop here, get some water, and happy to take any questions that there may be before we switch to the other thing. Yes.
Some of the time it happens that we are having lots of data and
Lots of data.
and lots of figures also. And we have to conclude it into 14 minutes.
Yeah.
Then that in that process, most of the time slide becomes bulky. A lot of the things.
Yeah, that's the challenge, especially in doing a PhD, right? You will have a lot of data. You just have to figure out what is more important, what is less important, what can be combined together, and what you can express, in a short but effective fashion. You have limited time. You don't want to stand there and tell stories upon stories of how that measurement was done. Instead, you can say that measurement was done in this manner, and let me jump to the results, because I think the results are a lot more interesting than the technique itself was. Right? This is entirely up to each one of you. You have to figure out how you will address your unique situation. This problem that Kulbhushan ji has said, almost every one of you doing a PhD and all that will face, that you'll have too much data to present in too little time. And you just have to compress things, prioritize things, eliminate some, put them in the backup slide so that you are able to talk about it if somebody asks. But just say, look, about this experiment, I have data in the backup slides, but in the interest of time, I will not talk about that. But instead, I will go to these more interesting simulations that I have done. That may be a good strategy to use. Okay? Yes?
Actually, when we are starting, we are having some outlines.
Hmm.
As you talk, sometimes it's better to not show.
Yes.
If it's not required, that's fine. But sometimes it's actually compulsory by template.
Okay.
So at that time, because already we are going in that same flow,
Yes.
and what things we should talk in the outline slide, and what things should not actually, and how much we should focus.
See, if having an outline slide is compulsory because your advisor asked you to do, or if it's there in the template, then certainly have an outline slide. What you should put in the outline slide depends on you, right? My personal feeling is that an outline slide should give the audience a roadmap of what you are going to present. And a good way to do that perhaps is through pictures. Why not have like research achievements and then have 4 different bubbles in which you have 4 different accomplishments from your PhD, each with a picture, and then say A, B, C, D. Let's start with A, then we'll come to B, then we'll come to C, and then we'll finish with D. Something like that. Okay? Keep in mind, what I am saying are merely suggestions. Each one of you has to sit down and think about your unique situation and what you think works best for yourself. What works best for you may not work well for you, and so on, right? But you've got to design your slides, think about it, and come to what you think works best for you. Okay? Cool. How to cite? Well, if your specific community or the lab has a specific format, then you should follow that. No, you have to refer it right there, I think. There is no point of referring to it in the very back, right? If somebody is really interested, oh, where did that data come from? If that reference is on slide number 45, they will never be able to make that connection, right? So you might as well, if this is a plot that you borrowed from somebody else's paper, just write here, you know, Smith 2022 or something like that. Any other questions or comments? Go ahead.
Like when we are putting some references, is hyperlinking necessary or not?
In giving a presentation, hyperlinking is not a bad idea, because if you have to somehow discuss it in more detail, then it is readily available for you at a click. So why not put a hyperlink? Sure. Yes. Question in the back?
Can we use one slide like 2 times to show if we are using like my schematic is for numerical work?
Yes. No problem. No harm done. If you think it helps in communicating that to the audience, absolutely, by all means use it again. Okay? Yes.
One problem we have, whenever we use any graph into the slides and we paste it in a picture format, the quality of graph always reduces.
Yes. So to do that, the practical tip is that in MATLAB, any fig file, most of you use MATLAB, I assume? Yeah? In MATLAB, how do you export it to PowerPoint? Copy paste?
Just copying and
No, copy paste is not a good idea. You can take a MATLAB file, a fig file, and you can export it to a TIFF file. And when doing that export, MATLAB allows you to specify the resolution of that TIFF file. If you export it with a 600 by 600 resolution, then pasting it into PowerPoint works very well, and it preserves the original resolution of the image. That plot I showed you, remember, one with 5 different colors, that was a TIFF file. So your standard technique of using MATLAB in PowerPoint should be to export every fig file as a TIFF file. It creates a new file, and TIFFs can be easily pasted into PowerPoint. Yes.
Like you said, introduction keeps the audience engaging with you.
Yes.
In the very first session. So when we are delivering the presentation for our defense,
Yes.
and we need to show more and more work
Yes.
within a confined time.
Yes.
So how much introduction should we add? Like how much literature we should
Sure.
learn? So
My feeling is that the literature survey should be very comprehensive. Especially I'm talking about this now in the context of a PhD dissertation defense. What is the point of a PhD dissertation defense? You are defending your ideas. You are saying that, look, I have added to the knowledge base. In order to be able to make that claim, you have to first summarize what the knowledge base was before you started, right? The audience, especially your committee, is interested in understanding the context of your work. Why did you even do that work? I did that work because somebody else has done this work, and I feel that he or she did not do this work, and I feel that that work is important for these reasons, which is why I will now present my work. You need to give enough justice to that first part to be able to then say that, look, my work is important, right? In my opinion, even if it takes 10-15 minutes for you to set the stage in a PhD dissertation defense, you've got to do that. But keep in mind, given the nature of the presentation, you should not be talking too much about the big picture. If I am giving a presentation on molecular dynamics simulations in lithium-ion batteries to an audience that knows about that field, I don't want to spend 3 slides saying that there is an energy crisis in the world and lithium ion batteries may perhaps save the world, etc., etc. Right? That kind of introduction is helpful if you're giving this presentation to undergraduate students. Right? But for people who already work in that field, who are very familiar with it, you've got to talk about it very briefly and then get down to the importance of molecular dynamic simulations in lithium ion batteries and spend most of your introduction talking about that rather than the big picture. Okay? Every occasion is different, so you've got to think carefully about your specific occasion and design it accordingly. Okay? Yes. I don't see a problem with that. I don't see a problem with that. Yes. Same title is just okay. Alright? Any other questions or comments? You know, we just ate and so I'm going through water. Okay, so what I will now do is that I will switch to the other thing that I want to talk about, and that is writing. So in addition to oral communication, the other way with which we communicate our ideas to the world is written communication. And that again, as a PhD student, as a faculty, it is something that we do all the time. You all in your scientific and engineering careers will always be writing something or the other. You may be writing reports, you may be writing manuscripts, books, what have you, you will still be writing. Okay, this is a tile from some market in Italy. I was there once, and this nice person was selling these ceramic tiles for different professions. So there was a firefighter, and there was a policeman, and there was a farmer, and they were doing their typical things, right? She had a tile for the professor, il professore. What was the professor doing? The professor was not running experiments. The professor was not doing simulations. The professor wasn't even teaching. The professor was writing. The point I'm trying to make is that writing is an integral part of my profession as a professor, and by extension of you all as somebody who's trying to learn and grow. Right? Writing is extremely important. It is an integral part of doing research. I would make an argument that if I go to the jungle and do some fantastic research, solve all the energy problems of the world, but I never tell that to anyone, then would I have even done that research? Would you consider that research to have even been done? I would argue no. I feel that in order for some research to have been considered as being done, others need to know about it. Others need to be told about it. And one common way in which we do that is by writing. We communicate to the intended audience through a variety of writing mechanisms: reports, papers, books, chapters, etc. And I would argue that your research is not done just when your measurements or your simulations are done. You're only, starting with a new chapter of your research, which is to write your research and communicate it to the audience. And towards that, I would say that the act of writing research, writing up your research, is almost as important as the research itself. And the two must go together with each other. These are not sequential things. These are things that must happen in parallel. While you are doing your research is when you should already be starting to write and generate new ideas for research, right? So it goes both ways. The research provides the fuel for the writing, but as you write, you realize that new ideas will come. You'll say, okay, I've written this. It would have been very nice if I can also explain this. And to do that, I have to go back and run a new simulation, right? So you go back and run that simulation, and research and writing therefore contribute and learn from each other. Okay, I tell my students, do not stop until you're done with everything to start writing, you should start writing when you're about 1/3 into your project. And that will help you greatly in the quality of your work itself. It provides a great motivation for doing the work. Because when you start writing is actually when you realize what you're doing and what is missing. Right? When you write, you're trying to convince the reader of a certain points. And when you write, you see that, look, there is a big hole here that I need to fill. I'm not able to convince them because I don't have this data. So let me go back and generate that data through measurements or simulations or whatever, and then come back and complete the story. You know what I'm saying? So today I will talk about some practical tips about becoming good writers. You will see that some of the tips I will share are similar to the tips I shared about presentations. Most importantly, the importance of practice. You can with practice become a good speaker, and you can with practice also become a good writer. Okay, I want you to think about what do we write. So just like I wanted you to think about who your audience is, similarly here, I want you to think about who is going to read your report or whatever it is that you're writing. Are you writing for your advisor? Are you writing for your peer group? Are you writing for some anonymous reviewer? Are you writing for the boss of your company? Are you writing for your customer? Or who the audience is? Because the style of your writing needs to recognize that and needs to be designed accordingly. Right? If you're writing a book for undergraduate students to do something, versus if you're writing a highly dense JFM paper that will go to the top person in the world for review, your style has to be different, right? So you've got to acknowledge that, and you've got to recognize the objectives of writing it. Why are you writing this? Who are you trying to convince? How will you go about convincing them about your ideas? And as I said, writing is very important as the research itself. You will be judged by the quality of your writing. We all read some very old papers, right? Have you ever read a paper from the 1960s? You may have. You read that paper, that person is long gone, but his or her work stays, right? You look at that paper and say, wow, what a nice paper this guy has written. His soul, wherever it may be, will probably feel happy about it. In that sense, writing is our legacy, right? After we are all done and gone from this world, what we write, what our name appears on it, will still stay here. And people will judge us on the basis of the quality of our work. That is the imprint that we will leave after we are all gone, right? Let that motivate you to write well. I don't want somebody 50 years later to read my paper and say, oh, what shabby work, right? I want them to say kind things about me through the work that they read from me, okay? And of course, you know, this is philosophical, this was all philosophical, but of course there are also some very practical benefits of writing well. If you write well, you will have papers published in top journals, you will get good jobs, you will graduate, you will get promoted, etc., etc. Right? It's a very important skill that will help you grow professionally, just like presentations. And as I said, your writing is your legacy. And now the question is, how do I write? Unfortunately, I do find that this is a common problem among students in general. Students don't write well. And I think that learning to write well is a part of the PhD process. During your PhD, not only are you trying to learn new experimental measurement techniques or new simulations or new math, at the same time you should also be learning how to present well and how to write well. Unfortunately, there is no magic wand for learning to write well. I can't just say, jump, 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 now you're a good writer, right? Unfortunately, it doesn't work that way. I wish there was a USB cable that I can connect to your brain and transfer whatever little I know, but that doesn't work that way. Each one of you has to sort of learn it on your own, and the best way to learn it is with practice. The more you write, the better you will get at it. If you're a new PhD student, the first paper you write, the draft, will probably come out pretty poor, right? And I'm sure all of you have had this experience that you sent something to your advisor and it came back more red than black, right? It has happened with me as well. I see some people smiling away. It can look very discouraging, okay? But I want you to try to see what your advisor did with all that red ink. What are the things that he was trying to tune? How was he or she trying to adjust the writing, right? Try to look at some few salient points of what is different about this writing than what I gave to him or her, right? Mimic the style of good writers. As you read papers in your field, identify 2 or 3 good papers that really impressed you, that you learned a lot from, as opposed to some really bad papers that were just blabbering around. Take those 3 good papers and try to follow the style of those writers. It could be your advisor or it could be somebody else in an entirely different part of the world. That's okay, right? They say, yeah, mimicry is the best way of flattery or something, some such English phrase, right? The best way to teach yourself something is to just follow something that somebody else is already doing very well. You're not copying them, you're just copying their style. And develop a good writing process. How do you write? Where do you write? Perhaps even that is important. Do you write in your hostel room? Do you write in the library? Do you write in your lab? Perhaps you will realize that one of these places just somehow brings out the writer in you much better. Maybe the lab is too noisy and the hostel is too many people coming in and out, but the library has a little nook where everybody will leave you alone and you can keep writing forever. Or maybe you will find that you write much better in the cacophony of the hostel room, right? Try it out and see what works for you. There isn't one right answer for any of this, but go figure it out for yourself. And as I said, your advisor can be a very good person to learn from. So take a look at the corrections, the edits that your advisor is making on your drafts and see if you can find a good big picture of what is going on. Why is he cutting out this line and replacing it with this? If you can follow the pattern, you will see what he or she is trying to do to your draft. Okay? I'll talk about the writing process. This is what I do for my writing and I find it to be very effective. So I want to share it with you. Whether it works for you or not, I do not know, but I want you to create a process for yourself. When I have to write a large manuscript about a paper that I'm writing, I don't just start writing. I first create an outline. It's a doc file. Of course, I write everything electronically. I think most of you do as well, right? So it's a separate doc file that just has a number of points that I want to cover in the different sections of the paper. So if I'm trying to write the introduction section of the paper, let me think about what my introduction section should cover. A roadmap, if you may say, of the introduction section. I will first figure out what the roadmap is. What are the important things that needed to be covered in the introduction section? Because I find that if I just start writing the introduction section itself, my mind will wander, meander, and I will not stay focused. On the other hand, once I have written this outline, then I can keep referring to that outline to make sure that I am being faithful to that outline, that I haven't just taken off in an entirely tangential direction and it's not what I wanted to write. Yeah, in that sense, I find it very helpful to create an outline. I also find it very helpful to create a list of figures that will go in my paper. Figures are the heart of the manuscript. Before I start writing the manuscript, I need to know what figures will go in this manuscript. I need to know that with a lot of detail, not just figure A, experimental setup, figure B, calibration plot. Calibration plot is not enough. I need to know exactly what the calibration plot will plot. What will be on the x-axis, what will be on the y-axis, how many curves will be there, what will be the values of the velocity at which I will carry out these calibrations. I would like to create a very detailed outline definition of each figure. Okay? This definition of figures is not set in concrete. It's not like I have to know exactly what figures will be there. I want to start somewhere, and then I am flexible enough to revisit my list of figures and adjust and change it if I feel the need to do so. But I've got to start from somewhere, is the point I'm making. Okay? A manuscript is a living and breathing document, right? It needs to adapt and change as you make progress in your research. And then, once the outline is there, just start writing. Okay? Especially early on, when I was younger, not that I'm very old, I used to have this problem that I say, okay, I now need to write something, my laptop is on, and I'm trying to write, and then my fingers don't move. I don't know what to write. Writing that first sentence takes an hour. Has that happened with anyone? Yeah? Yeah, getting started is the most difficult task, and it's not unnatural. Getting started, I have a stationary body. Getting it to move is the most difficult part. It takes the highest energy. Once it starts moving, you're only overcoming minor friction to keep it going, right? So my advice to you is just write anything. The first sentence that you write does not have to be perfect. You are always going to come back and change it, edit it. So to help you get started, just write the first sentence, even if it is not perfect. At this stage, it is more important to have something rather than to have the perfect thing. It's okay if your first draft does not look very good. As I said, more important is to have the first version rather than to have a perfect first version. Okay? I don't think it has ever happened with me that I write something and I'm done, it's ready to go. I actually will print it, edit it, then print it and edit it again, and so on and so forth. In fact, there have been some papers in our research. I keep changing the version number of the paper every day or occasionally in order to save old versions. There have been occasions when we've gone all the way to version number 68.0 before we were finally happy with the quality of the work and we sent it out. I'm trying to say that the first version is okay to not be perfect. It's more important to get it out there. Okay? Once you have the first version, edit it heavily. The first version always needs a lot of adjustments. The number of adjustments goes down dramatically as a function of the number of iterations. Right? The first iteration takes a lot and then it comes down, and by the fourth or fifth iteration you're making minor adjustments. Okay? At some point you get inputs from co-authors. You sent it to your the master student who helped you, or your foreign collaborator or your advisor, and say, I'm ready to get input from all of you. And ask all of them to use track changes so that you're aware of what is going on and work collaboratively. There are several tools like Google Docs, Overleaf, etc. that you can use for this collaborative writing. I'm a little old-fashioned. I still attach and send a doc file and they edit it and send it back to me, and it's a little painful. Perhaps I could do better using online tools, but whatever. In particularly, I don't use LaTeX, and the world is very polarized on that. You're looking at someone. Some people swear by LaTeX. They will give a dirty look to somebody who does not use LaTeX, right? For them, those who use Microsoft Word are an inferior species. Yeah, but I have my problems with LaTeX. I'm not going to go in here, but I'm just a Microsoft Word person. It doesn't matter. If you're a LaTeX person, may God be with you, good luck to you and all that. Just have a scheme and stick to it. The trouble occurs when a LaTeX person needs to write a paper with a MS Word person, and that has happened with me. Right? The LaTeX guy refused to write in Microsoft Word. He said, and I still remember, um, um, I can I can I can use Microsoft Word to write anything unless it is important. So I ended up basically editing on paper. So he would give me a PDF, I would print it, I would edit it on paper, and I would scan it and send it back to him. Say, okay, now take it and put it in your LaTeX. All right? Don't get me started, I hate LaTeX. The importance of writing is that, I think the most important part of writing is that your writing needs to be concise, dense, and to the point. You should be using minimal number of words. I tell my students often, in order to write an abstract, I tell them, go write an abstract. They write the abstract, give it to me, 500 words. I say, okay, now go back and write the same thing in 200 words. And it's not easy. But then when they write it in 200 words, I say, okay, now write it in 100 words. It's always possible to do it. It just takes a lot of time. But even this very simple practice of taking something that you have yourself written in 500 words and trying to rewrite it in 100 words is very illuminating. Because you have to make compromises, you have to make decisions about what to write and what not to write. And you have to think about how I can possibly combine 3 different sentences in one single sentence. Right? I think that's a very useful exercise that I would recommend you all to do. Okay? I'm a big fan of minimalism when it comes to writing as well. The more important thing, flowery English is not important. What is important is a laser sharp focus on the intent. What are you trying to convey to the audience? Right? What is the big deal about your work? And of course, your writing needs to be supported by figures of the highest quality. No cutting corners there. If you were to come and work for me, you will hear horror stories of how I looked at a plot and I said, you know what, that's not the correct red color. You've got to go back and use the right red color. All right. I am laser sharp on that, extremely important in my opinion, and I think you should all be as well. Figures have to be the best possible quality. Your writing needs to be supported by good references, and your writing should not have grammatical errors. Okay? Your writing should have consistent style and font, and I recommend Times New Roman 12 point font size. Okay? And of course, your writing should not be plagiarized. And these days, with all the automated plagiarism detection tools, it's very easy to catch plagiarism. So you should be writing from scratch. You read something, put that away, and now write entirely in your own words. You're not going to go very far if you just copy and paste from somebody else. It will simply not work.
Whatever we have published and we are writing the similar thing, simple thing.
Yes, yeah, so
Our work also.
yes, so self-plagiarism is a problem. I've written a paper on a topic and I'm now writing a follow-up paper on the same topic. I'm going to have to use the same references, roughly the same motivation, etc., etc. Same equations as well. Even there I say, read your previous paper and then put it away. Just put it away. If you also start writing from scratch, it will still be sufficiently different from the past work. I'm just asking you not to copy paste. I feel if you are yourself going to make an honest effort of writing from scratch, you will be okay. Of course, since these anti-plagiarism tools are now readily available, you can check plagiarism yourself, right? And it will tell you exactly where the problems are, and you can go back and fix those specific places. Okay? All right. So I'm going to talk about a typical journal paper and share my thoughts about how a journal paper is organized. Okay. Sorry, this is a little too small to see. If you would like, feel free to come forward. Can I zoom into PowerPoint? No. No. Anyway, the actual language is not important. I'm trying to give you a big picture of what a journal paper looks like. Okay. First of all, you have an introduction section in which the first paragraph is a very general introduction to the field. So in this paper, we had done some imaging, infrared imaging of 3D printing process, but in the very first paragraph, I am giving a very broad introduction to what 3D printing is, right? And what are the different types of 3D printing processes, and what is the state of the art in that field. Having done that, sort of like the grandma paragraph, I can call it the grandma paragraph. After that, I start talking about what others have done in this field, right? So I'm saying temperature measurement with this has been done, an IR camera has been used for this, a theoretical model has been developed, etc., etc. There are some spelling mistakes which I should fix as I go, and so on. I'm giving a rich, a dense, comprehensive overview of the related literature in this field to show that I know what others have done. Okay, and after that, I identify what the gaps in the community or in the literature are. I say, in contrast to side view measurement presented in these papers, there remains a lack of experimental measurement of this. And then I justify why this measurement is important. I say that side view measurements are good, but on the other hand, blah 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 cannot be understood from the tools available in the literature. Right? I'm trying to create a justification for my work. I'm trying to identify the hole in the literature that I am going to fill with my work. And then in the end, I'm saying, given the importance of side view measurements, I'm saying, based on the literature survey that I have shown and the gaps identified, this work presents an alternate approach for measuring blah 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 blah. In general, the introduction section is probably the most difficult to write. It takes a lot of work to compress a lot of information. It's much easier to write the experimental setup. You know what the setup is. You can easily describe it, right? Writing the introduction section takes a lot more effort. So the rest of the paper is actually much easier to write. For that purpose, my students and I usually start with these easier things and then jump on to the introduction section later. We don't write in sequence. You don't have to, okay? Then in the results and discussion section, I would like to see a coherent, dense, scholarly discussion of the material supported by good quality plots. So this discussion is very dense, and I talk about a bunch of things that are going on. I need to go back. Actually, I found it. And towards the end, I conclude. How are we doing on time, by the way? Since I'm full screen, I'm not able to see the time.
4 minutes.
Okay, all right. So towards the end, I will conclude and I will give a summary of my research. I will give some future directions for the work and I will finish up there. Okay. It's important to make good plots. I think I've said this already, so I'm not gonna focus too much on it, but just to summarize, make your plots in MATLAB. The font size should be sufficiently large. Use lots of colors and line styles and create rich, happy looking plots rather than just one straight line. Okay, and as I was saying, generate a high quality image file, a 600 dpi TIFF file that you export out of MATLAB before you paste into your PowerPoint slide. Sorry, into your manuscript. So again, the same example. This looks much more beautiful than that one. Writer's block is a well-known disease. We all sit down, stare in front of the computer, determined to write. I'm going to spend all day writing and I'll finish writing 50% of my dissertation today. And the reality is you sit there at 9 o'clock and by 11 o'clock you've written one sentence. Okay? If that happens with you, you're in good company because writer's block happens to almost all people. What can you do about it? My suggestion is to write something. Just write a sentence. Just get started. It's getting started that is more difficult. So if you start by writing one sentence, the ideas will then begin to flow. Okay, it is overcoming that first step that is extremely important. One thing that helps me very well is to set up short sprints of writing. I never tell myself, I'm going to write all day and I'm going to finish half this manuscript today. Instead, I tell myself, look, it's 9:15, I have a meeting at 10 o'clock. I have 45 minutes. I will stop everything else. And in 45 minutes, for only 45 minutes, I will write as much as possible. So for a short amount of time, I am committing myself to ignore everything else that is happening in the world and only write. I find that that itself helps me write quite a lot. Oftentimes, almost always, I exceed my expectations out of those 45. I take some measurements, read other stuff, go take a class, whatever, and also write. I'm not a big fan of having a writing day. It's better to set realistic goals than be unrealistic. Okay? You're not going to write 50% of your dissertation in a day. But if you say that, look, I'm going to write 5 pages today, good quality writing, and if you get done, celebrate at the end of the day and give yourself a little treat for having met your goals. Okay? Again, practice is the most important thing. The more you practice, the better you will get. It is an integral part of your research. It's not like you do your research and then you write. You have to write in parallel with your research or your technical work. Just write, you will get better and better with practice, and if you put in a concerted effort, exclusive, focused, short sprints of writing, I can clearly see that you can write much better. Okay? And again, to go back to a point that I made early on, identify a few good people whose writing you have liked, see what they are doing, and see if you can also follow that style of writing. And again, importance, figures are extremely important. So pay a lot of attention to the quality of figures in your work. Okay? So with that, I'll finish here. Happy to take questions and wish you all the best in your academic journey of writing and presenting. Thank you. I think there's some snacks outside, yes? Are there snacks outside?
I just came to ask you, I don't know whether somebody has asked.
Yes.
What's your take on students using ChatGPT for writing?
I'm not a big fan at all. No, you're not doing justice to yourself, because ChatGPT can certainly help you write. But what is the point of writing? The point of writing is to become a good analyst. You're trying to analyze something. You're trying to refine something. All right, folks, let's get started. It's been a long day, including heavy food. So thank you for still being here and still being awake. You guys are awesome. Nobody has actually slept away. I didn't hear any snoring so far. And a 5-day intense short course like this is not easy to handle. So good job everyone. We are almost there. So in this tutorial, I want to talk about temperature measurement. We have been talking quite a lot about experiments, and so I think it makes good sense for me to discuss how do we measure temperature. Of course, this is in the context of lithium-ion batteries, but what I will talk about is very broad, and temperature can be and needs to be measured in a wide variety of devices. Okay, so the first question is, how do we measure temperature? What are the different techniques to measure temperature? Can we make a list? Can each one of you maybe contribute one way to measure temperature? Thermocouple, okay. So let's say thermocouples. What else? Keep shooting, please. Anyone? Thermometer. The word thermometer means a device that measures temperature. So I want you to be a little more specific. Expansion, sure. So I will say expansion based. Maybe I can redefine my list. I am asking you what are the different ways in which temperature can be measured. So this is by measuring a potential difference due to temperature. This is by measuring expansion because of temperature. What other effects can be used to measure temperature? Change in what? Sorry, length? That is expansion. How about change in resistance? How else will I measure temperature? I have a body, I have this.
Heat exchange.
Heat exchange is a very good one. If I have something and I want to measure its temperature, I have nothing else in the world, what will I do? I have only myself. I will touch it, right? I will touch it and I will feel, does it feel hot or does it feel cold? So actually touch itself, sort of a biological way of measuring temperature. Something happens to my cells when I touch them to a hot body or a cold body, which allows my mind to sense temperature, right? And it turns out that biological sensing is actually very good. People have done measurements in which they took fish and put it in a tank where the temperature changes from one end to the other. The fish all congregated to one particular temperature where they were most comfortable with an accuracy of about 0.1 degrees Celsius. So that's very remarkable. Okay. By the way, our sense of touch in terms of measuring temperature can be very misleading. Imagine in this room I have this doorknob. If right next to it there was a doorknob made up of wood and I touch both of them, which one would feel cold? Huh? The metal one, right? Floors. If I have a tiled floor versus a wooden floor and I walk on, without shoes and socks, it feels very different, even if they're at the same temperature, right? These two knobs are at the same temperature, but the metal one feels colder. It is because when I touch something, my body is at 37 degrees Celsius, this is at 25 degrees Celsius, that temperature difference causes a flow of heat. My hand begins to lose heat. And my body does not measure temperature, it measures that loss of heat. It senses that I'm starting to lose heat from my fingers. This body must be very cold. Unfortunately, how much heat I lose is not only a function of the temperature difference, but also the properties of this body. It's called effusivity. Effusivity of metal is different from that of wood. That is why that is different. Anyway, what are some other techniques with which I could measure temperature? Huh? Change in pressure? Yeah, sure, why not? Change in pressure. How would that measurement technique look like? What would a pressure-based temperature sensor look like? It would simply be a cylinder filled with some gas, a fixed volume cylinder, right? With a pressure measurement device. As I take it here and there, if the pressure in this cylinder changes, then I will know that the temperature has changed. Provided two things, the volume is the same and it is an ideal gas. Because for an ideal gas, we know PV equals nRT, volume is the same, the mass is the same, pressure is in fact proportional to temperature. Right? I can easily see how the temperature changes because of changes in pressure. What else? Maybe one more item? Huh? Optical, yes. So changes in optical behavior. You'll see here, thermocouples is changes in voltage. You'll see here that in each case, we are not measuring temperature directly. we are measuring the change in something else because of the change in temperature. It's an indirect measurement of temperature. I don't think anybody really measures temperature directly. We all measure something else that changes because of the change in temperature. Yeah? Question? Comment? Okay. So in today's brief lecture, I want to talk about a few of these techniques, but more importantly, I want to talk about what constitutes a good measurement. In the previous lectures, remember I had said that I don't want to say that the temperature of this body is 35.2 degrees C. I want to say it is 35.2 degrees C plus or minus 0.2 degrees C. This quantity, which is called the uncertainty, communicates that, look, I have measured it to be 35.2, but it could very well be plus 0.2 or minus 0.2 of that. Where does this number come from is something that I want to think about. If I measure a temperature of 35 degrees C, is it really 35 degrees C, or could it be off by 0.1, or could it be off by 1 degree C? How much of an effort do I need to make to measure temperature with an accuracy of 0.1 instead of 1 degree Celsius? There are some scenarios in which measuring temperature with an accuracy of plus or minus 1 degree C is acceptable. Right? Can you think of a scenario where plus or minus 1 degree C is okay? Building ventilation, 1 degree C is quite okay, you know. Whether the temperature of this room is 25 or 24 doesn't matter to me. Right? In fact, most devices measure temperature or report temperature to plus or minus 0.5, I think. Right? And in the US, where we work in the Fahrenheit scale, the accuracy there is 1 degree Fahrenheit. Yes, and half a degree Celsius temperature change is roughly 1 degree F temperature change. But there are some other applications in which I want this to be much more accurate. If I am designing a spacecraft going into space and it's a really delicate experiment, it is not enough for me to measure it to plus or minus 1 degree C. It needs to be a lot more accurate. So let's think about these issues and how do I design an experiment in an effective way in order to get good confidence in my measurements. And for that, the example that I will take is that of a resistor. So here is a resistor R0, metal resistor. Okay, keep in mind not the colorful resistors that you see in electrical labs. Those are carbon based resistors and they have been designed to be temperature insensitive because they want to put them on a device and then in a car perhaps, and as the car goes around, you don't want those resistances to change with temperature, right? Those resistors, the colorful cylindrical tiny little resistors are not good temperature sensors because their resistance is not going to change with temperature. Instead, I am looking for something for which there is a significant change in resistance as a function of temperature. In other words, if I was to plot resistance versus temperature, if I have one resistor that looks like this, that's a poor temperature sensor. You see what I'm saying? That one is a poor temperature sensor. I would like to see something like this. I would like to see a linear increase in resistance with temperature. I don't want it to be non-linear either. A plot like this is not desirable either because after some point the resistance will go up so much that I may not even be able to measure it. Even a 1 degree Celsius change in temperature and the whole thing shoots off. This is the ideal temperature sensor for me. So if you go to a shop and online usually these days and you have several candidates, you've got to make a good decision about what is a good temperature sensor for you. Okay? Then beyond that, suppose I go and purchase this temperature sensor. It looks like a thin sheet with two wires coming out, and I attach it to the surface of interest. What do I do next in order to measure temperature of that surface? Tell me. This surface is getting hot, and I am interested in measuring the temperature of the surface based on this resistor. What's the next step I should take? Let's attach it. So, and we have discussed this at great length previously. How do I attach it itself is an important question. Yes. Where to? Exactly. And how to attach? Do I just put it there and press it with my fingers? Or do I put some epoxy between them and attach it? Thermally conducting, but electrically non-conducting. Exactly. So you can't use a metal paste or whatever which will short things around, right? Then what do I do? How, let's take a step back. How are we proposing to measure this temperature? By change in resistance. So I must measure the resistance of this body, and that will tell me the temperature of this body, right? That itself is not straightforward. How will I measure resistance? Can somebody propose to me a way to measure the resistance of this sensor? Fair enough. In order to measure a resistance, I must measure. Exactly. Yes, absolutely. Yes. So, sure, yes. So, our original task of measuring a temperature was sort of subcontracted to measuring resistance, which has now further subcontracted it to measuring voltage, right? So, I need a current source and then I need to attach a voltmeter in order to measure that voltage. How much current should we send through this thing?
It should be minimum, and that resistor should be highly sensitive.
It should be?
It should withstand the DC current.
Yes, yes. No AC. Let's stay away from AC. We'll send a DC current, and the question is how much DC current, and one comment was minimum possible.
Minimum possible, but and the resistor which we are using, it should be highly sensitive towards the.
Sure. So the sensitivity of the resistor is usually measured in terms of this alpha term, where alpha is the temperature coefficient of resistivity, right? Alpha should be as large as possible. So if for a certain delta T, delta R is alpha R naught delta T, right? And if this is my change in resistance, the change in voltage will be how much? It will be I times the change in resistance, and that would be alpha I R naught delta T. When I design this experiment, should my delta V be large or small? Delta V. Suppose I am trying to measure a change in temperature of 0.1 degrees C. I am ambitious here. I want to measure a change in 0.1 degrees C. The resulting change in voltage, should it be large or small?
So that if there is change in 0.01, then we can configure that.
Yes, absolutely. I would like this to be large enough to be measurable. If the initial voltage was 10 volts, and if it changes to 10.00001 volt, that would not be easy to measure. But if it changes to 10.1 volt, that is much easier to measure. I can measure this also, no doubt. It will just take me a much more expensive voltmeter, the reading of which goes all the way to the 4th decimal, right? Instead, if I need, all I need is a change in the first decimal, that voltmeter is much cheaper and easier for me to use. I can even do it using a handheld voltmeter perhaps, right? So I am interested in increasing the value of delta V as much as I can. What do I need for that? I need alpha to be large, I need I to be large, and I need R naught to be large. Alpha is not in my hands. Alpha is a property of the material, right? I can perhaps go and look at candidate materials to design this. Let's do that real quick. It's a useful exercise. So thermal coefficient of resistance of different materials. Let me see if I can find a table. Table. This is a good one. Is it easily visible in the back? So what do we see here? First of all, the temperature coefficients are very low. The units, it doesn't give you a unit, it does, per degree Celsius. So every degree Celsius, the resistance of nickel changes by about 0.6%. Nickel that had a resistance of 1 ohm at this temperature, 1 degree C later will have a resistance of 1.0059 ohms. It's a very It's a very small effect, right? But nevertheless, there are some materials that have reasonably high temperature coefficient of resistance. Nickel being one of them, iron being one of them, and so on. I want to stay away from these guys. And by the way, these alloys that have extremely low temperature coefficient are designed that way. They put the right proportion of the mixture, whatever their constituents are, in order to make sure that their resistance does not change with time, because with temperature, because those are used in heating elements, and you don't want the amount of heating happening in the element to itself change as it gets hotter and hotter. In fact, the same thermal runaway problem, right? If this temperature coefficient of resistance is very high, then what will happen is it gets hot, its resistance increases, so it generates even more heat, because of which it will get even hotter and so on, right? That is the reason why these numbers are designed to be so low. But anyway, in order to design my temperature sensor, I would like a high value of alpha, and so nickel or iron are probably good candidate materials for that sensor. In addition, the other thing that I can think of is I, the current. This tells me that I would like to have as high a current as possible, because the larger the current, keeping everything else the same, the larger will be the voltage difference produced, the change in voltage, and it will be easy for me to measure it, right? Should I use a very high current? Yeah. The problem with using a very high current is that if I send a large amount of current through this sensor is a resistor after all, it will generate its own heat.
It will short also.
It won't short. Why will it short?
Generally, when temperature become high, then the resistance properties they lost.
Sure. So I'm not sending a ton of current, right? I'm not sending an unrealistically large amount of current, but nevertheless, at large currents, this resistor will generate its own heat, And so the local temperature that I want to measure here will get affected by the sensor itself. It's like I am trying to measure something and I am changing it in the very act of measuring, which is what I don't want to do. I want my measurement to be as passive as possible. Okay? They say that even the act of looking at something changes it. Why? Because when we look at something, we shine light on it, we are shining photons on it. A photon is going to go and hit the thing that I'm trying to measure, and it will not be the same thing ever again. Right? It is impossible to measure something completely passively. All we can do is to try and minimize our impact on that thing that we're trying to measure. So typically here, the way we think of it is that I am going to use the minimum possible I current that gives me just the amount of change in voltage that is measurable with my instruments. I have an instrument, it reads voltage to the second decimal. I will only send that much current which produces a change in voltage to the second decimal. If it produces a change in voltage to the first decimal, I'm sending too much current. I don't need that much. So I'll slow down on the current in order to get a more reasonable change in voltage. This phenomena is called self-heating. And I want to minimize self-heating. Okay? Now, you went to that table that I showed, you picked up the value of alpha from there, you know your initial resistance, you stick it in here and you find out change in voltage, right? And back calculating, you find out the change in temperature. That is typically actually not how it is done. Typically, for any temperature sensor, I'm talking about all of this in the context of resistances, but this is true in general. In general, for temperature measurement devices, we have to always carry out a calibration. What is a calibration? It's an experiment done in advance of the real experiment to sort of teach the sensor what to expect. Or, in other words, if I flip it on its head, to teach ourselves how to interpret the output of the sensor. So, for example, if I have a temperature measurement device and I want to use it to measure a temperature in the range of 20 degrees C to 50 degrees C, then even before I start taking my measurements, I need to expose it to known temperatures of 20 degrees C, 25 degrees C, 30 degrees C, 35 degrees C and so on. And at each of those known temperatures, I want to measure the voltage that it is producing. So in other words, I want to create a plot of voltage versus time. At 25 degrees C, I read a voltage. Then I repeat this measurement at say 27 degrees C, and I repeat the measurement and I get this number. I run this calibration at a number of data points, and I have been able to get what is known as the calibration curve. Why is this calibration curve important to me? Because this calibration curve is my key to converting any future measurements of voltage into temperature. Right? Having taken these measurements, now I am confident that if I run my actual measurement and if the voltage turns out to be this, then the corresponding temperature is this much. You know what I'm saying? The quality or the uncertainty of my actual measurement depends critically on the quality of my calibration. I cannot measure any more accurately than the accuracy of my calibration. If I calibrate it only at a few points, I calibrate it at 25, then at 30, then at 35, and then at 40, then I cannot report the temperature measured to be 26.3 degrees Celsius. My calibration was never as accurate to be able to tease out the first decimal here. I also cannot use it to measure a temperature of 18 degrees Celsius, because 18 degrees Celsius was never included in the range in which I measured the temperature during calibration. Okay? And the big challenge with calibration is that it requires me to provide a well-known temperature of 20, 30, 40, etc. degrees Celsius. Whereas, why did I start this process in the first place? I started this process in order to measure a temperature, right? So, essentially the point is that in order to measure something, I need to calibrate, for which I need well-known sources of that thing itself. I need to have a body at 25 degrees Celsius, and then I need to have another body at 30 degrees Celsius and 35 and 40 and so on. In other words, before I go and measure the temperature of this body, I need to have a hot plate whose temperature I can control and whose temperature I can measure with great confidence. Then I will take my sensor, I will stick it to this hot plate, I will set the hot plate at 25, measure the resistance or the voltage, set it at 30, measure the voltage, set it at 35, measure the voltage, and so on, and thus create a calibration curve like this. And then, having created the calibration curve, I can now come here and take my actual measurement. There is no point of going directly and taking a measurement unless I have a calibration. Oftentimes, when you buy this sensor, the manufacturer will provide you a calibration. They will give you this chart that I drew in the next slide, or they'll provide you an equation between the voltage and temperature. But if you are a systematic, if you want to stay in control as an experimentalist, if you're very particular, you will carry out a calibration yourself. You will not depend on what the manufacturer is telling you. Of course, it becomes challenging because I said that I need to have a hot plate with a very well known temperature in the first place. How do I know the temperature of the hot plate is correct? Because the manufacturer has calibrated that hot plate against something else in their labs. And how are they confident that they have done it correctly? Because their calibration source has in turn been calibrated against something better. In fact, you can take this chain all the way back to some very well known standards of temperature that NIST, the National Institute of Standards and Technology in the US, maintains. NIST maintains standards of length, standards of temperature, and standards of all kinds of other things that we need to measure. So somewhere in Paris or wherever, there is a bar that has a length of exactly 1 meters. You can use that bar to calibrate a scale. That scale can be used to calibrate other scales. And strictly speaking, the scale that you use in your lab should be traceable all the way back to that well-known standard 1 meter rod. That entire tracing back is probably too much to expect. But at the very least, you should do step number 1, which is that you have a good quality hot plate, perhaps brand new, from a good manufacturer, and you trust it, right? You carry out your calibration at multiple temperatures on that hot plate. And then you have this calibration chart, which can be used for good accurate measurement of temperature. Does that make sense? Any questions?
How we can
How do we calibrate a thermocouple? Well, what is a thermocouple to start with? A thermocouple is a device which comprises two different metals in wire form that are welded to each other at the two ends. And the property is that certain pairs of materials, if there is a temperature difference across, then that causes a voltage difference between the two ends. So you sit there, measure the voltage difference. If these two are exactly at the same temperature, there is no voltage generated. But now if this thing begins to heat up, you've taken this thermocouple and you've attached it, one end of the thermocouple is attached to some surface. The two metal wires are coming out. As this bead, thermocouple bead, gets hotter and hotter, a potential difference is produced. And there is a linear relationship between delta V and delta T. So as the temperature difference changes, the voltage changes as well. It's a linear relationship, and in order to be able to have confidence in the thermocouple measurements, you need to derive this calibration plot yourself. You need to take your thermocouple, stick it to a hot plate, and then slowly increase the temperature of the hot plate. At multiple temperatures, allow steady state to reach, and at that steady state measure the voltage difference produced by that temperature. And you run it at multiple temperatures, closely spaced intervals, and you get this plot. Once you have this plot, then you take your thermocouple out and you can go wherever you want and measure a voltage. Suppose you measure this voltage, then this plot tells you that the temperature must have been that. You know what I'm saying? In principle, this curve can be obtained only by 2 points. In principle, you can take one measurement here and one measurement here and join the two and you are done. But really the accuracy of that line gets better and better if you have more and more points through which you can fit that straight line. Even small, if you have only 2 data points, even small errors in these 2 data points can cause your line to shift dramatically. Whereas if you have a large number of data points, then small changes in one of them does not really change your line dramatically. That is the reason why it is recommended to calibrate at a large number of data points before you finalize your calibration curve.
We use the ice and water.
Yes.
And put it into the ice.
Yes.
And the temperature, whatever temperature is coming,
It's said to be 0 degrees C. Yes. And on the other hand, you do it with boiling water. Yes. Unfortunately, there are not a lot of other standards between these two temperatures, right? So, excuse me, in the lack of anything else, you use those two to determine this curve. And what can you do? But if you have a good hot plate, then it's never a bad idea to calibrate it at multiple points with the hot plate as well. Question?
Actually, as you were saying that using this interval of 5 degrees centigrade over here,
Hmm.
and are we sure that this 26.3 degrees centigrade is okay or not? Like, what should be the minimum voltage range that we need to capture, like for 20 degrees centigrade of temperature change?
Yes, so are you asking me, in order to get this type of accuracy, at how many points do I need to do the calibration? I would say that if you are going down to the first decimal point, then your calibration should also have been done with plus 0.1 degrees C. So I'm asking too much here, but you should be doing your calibration at 25.0, 25.1, 25.2, and so on degrees Celsius. Okay, most people don't do that much, you know. I think that If you're going down to 0.1 degrees C, it is perhaps okay to measure at 25, 26, 27, 28, 29 and so on. Sometimes we do it the right way and sometimes we are in a hurry.
The experimentalist will always make many sensors to do calibration.
Yeah, but calibration is a holy thing, you know. You cannot proceed forward without a good calibration. Yeah, exactly. If you're doing measurements at high temperatures from room temperature to 500 degrees C, you cannot calibrate with plus minus 0.1, right? But then, to be fair, for high temperature gases, you never also report the temperature to be 750.2 degrees C. 750 is good enough, right? Sometimes even accuracy of plus or minus 10 degrees C is enough, right? At that temperature, does it really matter if the gas is at 740 or 750? It doesn't, right? So in that sense, in that range, you can probably calibrate every 10 degrees C or every 20 degrees. I think the general point that I'm trying to make here is that measuring something is very easy. All that it takes to take this measurement on this surface that we talked about is that you stick it in there, pass a current, measure a voltage and you're done, right? But in order to ensure the quality of that measurement, it takes a lot of background work and effort. Before you even go to the lab, you need to think hard about it. There are a lot of choices to make. What material should I have? What current should I pass? Etc. etc. You go to the omega.com website and they will throw you 100 different temperature sensors. Which one do I choose? How do I attach it there? These are all thoughts that you need to plan in advance. You don't want to just show up and attach it, you know, with a stapler or something like that, the first thing that comes in your hand, and then just take a measurement and go away. You will never have confidence. You will never be able to convince others about the accuracy of your measurements. In your presentations, if you show the calibration plot and if those points are very closely spaced, done. People will never question anything else that is going on in your measurements. If on the other hand you just show the temperature measurement, and especially if you say that my temperature was measured to be 26.329 degrees Celsius, if you report that, that is what sets up a lot of alarm bells. If somebody is claiming to me that he or she measured the temperature to be 26.329 degrees C, then please show me how you're so confident as to go up to the third decimal. Maybe you are, but I need to see. Before I'm convinced that the temperature was as accurate as that, I need to see evidence that it can indeed be measured that accurately. I would much rather see somebody say that the temperature I measured was 26 plus or minus 1 degree C. Remember the thing about those who know that they don't know. At least this person knows that he or she does not know. Oftentimes that is enough. Okay? Short discussion today. I'll probably finish here since we are all tired. But I just wanted to communicate the importance of putting a thought process behind measurements. I can't just show up and take a measurement. I have to design it well. I have to think hard about it. I have to make choices. You know, consciously I have to choose the right things in order to ensure the success of my measurements. Alright, we'll stop here. It's been a long day. Thank you so much for still being here. Tomorrow is half the day. Good news, and Dr. Tyagis already said a few things about the exam. So have a good restful night, and I'll see you again tomorrow morning. Okay, thanks again.